All right, let's check for sound. Do I hear myself? Looks like I do. Yep, sound is coming in. Next, check for visuals. Do I see my hand moving around there? Yes, I do. Okay, perfect. Then we are good to get started. Let's go ahead and put these headphones away. And let's begin the final chapter for AP Physics 1. Let's begin the topic of fluids. Do I have the back of this sheet available? Yes, I do. Perfect. So yeah, sorry for the delays. I know it's been almost 2 weeks, actually maybe more than 2 weeks. I don't even remember the exact day when the last stream was, but yeah, sorry for postponing this so many times. Part of it was just, even now, I still feel like there's some more preparation that could have been done. I'm just not sure what it is. I just have this feeling that there's something missing, something that I have forgotten to prepare, and I don't know what it is. I've looked over the chapter multiple times. It's not a particularly hard chapter. It's just a topic that I rarely get to teach because there aren't that many students who were taking AP Physics 2, and up until this year, this topic was a Physics 2 topic. So yeah, I just feel like no matter what I do, I won't be satisfied with the end result with this chapter. I just feel like I could have used some more experience listening to frequently asked questions from students that I never got. So I'm expecting to see a lot of gaps. Like if I end up looking at this, I don't know, 5 years from now, I'm gonna find all sorts of things where it's like, oh, you forgot to mention this, you forgot to mention that, blah, blah, blah. But the show must go on, so I've taken a look at some problems, and I think I've found some good ones. There were some problem types I couldn't find in my book that hopefully I will remember to do. I did make some notes, but did I actually make some notes for, let's see. Yeah, actually I did, for 2 problem types that I did not find among my textbook problems. So yeah, and if you saw the schedule, I think I have been able to cleanly split this into just 2 sections. Fluid statics, which is just going to focus on fluids not moving today, and then next time will be fluid dynamics, fluids in motion, and that should be all we need for the chapter, hopefully. So without further ado, let's begin. Let's begin the topic of fluids. So to understand fluids, the first thing we need to do is talk about the states of matter. If you're good with your chemistry, then this is going to be really basic stuff. If you've never done chemistry before, I don't know how that's possible because this is stuff that I learned in like 5th grade, but solids, liquids, and gases. And yes, I know there are more states of matter than just those 3, but these are the 3 that we encounter in real life the most. Solids, liquids, and gases. If we look at these things at an atomic level, here's what solids look like. Solids look like a bunch of atoms that are packed really close to each other. They typically have a definite shape, although we can easily come up with examples of solids that don't necessarily have a definite shape, or rather, they're not rigid, is what I would say. But if you don't apply some sort of force to them, or some sort of stress would be the term that you may have come across if you did the reading in the book, then they will typically just maintain their form unless subject to some sort of external force. So an example of a non-rigid solid would be something like a sponge or a rubber band. They are solids, but also they're flexible. Their shape can change, but for the most part, in the absence of any sort of external stresses, solids have a definite shape. Have a definite shape. And also their atoms tend to be very densely packed. Liquids, on the other hand, if you look at them on the atomic level, their atoms are a bit more scattered, further apart. They're not as tightly connected to each other. They can slide past each other. They can, this atom over here can weave its way in between all the other atoms, assuming the other atoms stay still, which they won't. They kind of move around like bumper cars, I suppose. But yeah, the atoms in liquids have the ability to just move past each other, and that allows them to flow. Gases can do a similar thing, and more easily, because the gaps between atoms of gases are just much wider. There's barely any attraction between these particles, so they don't really tug and restrain and pull on each other that much. But because liquids and gases have this ability to have their atoms move past each other really easily, because they have this ability to flow, they are both grouped into a category that we call fluids. So fluids are actually just liquids and gases. Fluids is just a more inclusive term that includes both liquids and gases. Most people think of fluids as only being liquids, but gases are actually part of that category. Most of the fluids we'll be looking at are going to be liquids in this chapter, but we will see some things with gases here and there. So what do liquids and gases have in common apart from, having this ability to flow? Apart from having this ability to flow, liquids and gases also have a non-definite shape, have an indefinite shape. They just take on the shape of whatever their container is, have an indefinite shape, have an indefinite shape. Same for gases, have an indefinite shape. But that's pretty much where the similarities stop, because there is one major difference between liquids and gases. Gases have an indefinite volume. Gases have an indefinite volume. Have an indefinite volume. Another way of saying this is that they are compressible. You can take a tube full of gas and then you can squeeze, if there's if you have like a syringe. And I'm not talking about a syringe with a needle tip. I'm talking about just like a bike pump is the better way to think about it. You can take that, you can fill it with air and then cover up the the tip, the end of it. You can cover that up and then push the piston down and it will move down. The volume of the gas will change. Gas will not leave because you're blocking it from leaving at the tip, and it's blocked at the top where the piston is. At least it's supposed to be, unless it's broken or something. And the gas will just have to shrink in volume in order to allow the piston to move down. So gases have an indefinite volume. They are compressible. while liquids rather, have a definite volume, as do solids. Have a definite volume, as do solids. Although there is a bit of an asterisk because it's not entirely true. You can apply stresses to fluids and even to solids. It's a little bit harder, but you can apply stresses to liquids and solids where you can actually change their volume, although there are limits to it. So what we are going to be dealing with, a term that we might see, or at least what we will assume whenever fluids are mentioned here, unless we're explicitly told otherwise, we will be assuming that we are working with ideal fluids. Which are fluids that are non-compressible. Fluids that are non-compressible, that's the first thing. Fluids that are incompressible is probably the more official term. That are incompressible. That's one requirement. That's one assumption when we call something an ideal fluid. And non-viscous. They lack viscosity. What on earth is viscosity? Viscosity is stickiness. Compare something like water to something like honey or molasses or, I guess, concrete before it dries. Right? Some liquids flow a lot more easily. They are less sticky. The liquid particles don't stick to each other as much, whereas other liquids flow a lot more quickly. The molecules don't stick to each other as much. So that's what viscosity is. Viscosity, you can think of it as the stickiness of a liquid, and if you want to learn more about this stuff, you can of course go watch whichever one of my old chemistry videos focused on this topic. It would have to be what was it? It would have to be in like the intermolecular forces video that I did. It might have been like part 11, 12, 13, somewhere around there of my chemistry playlist, if you're curious about that stuff. What did I title it? I think it was Reading Between the Molecules, because it was a chapter focused on the forces between molecules as opposed to the forces within molecules. But now I'm just going off on tangents. So let me see. Is there anything I haven't mentioned yet about these three? So we've defined solids, liquids, and gases and their main properties. Gases are the only ones that we consider to be compressible, although technically you can somewhat alter the volume of solids and liquids. They do have some compressibility, just not much. If you tried to take this, if we go back to this example of a syringe or a pump, and instead of filling it with gas, you fill it with water. If instead of filling it with gas, you fill it with water or some other liquid, and then you force it shut over here, and you try and push down on this piston. If you try, then one of two things will happen. Either there will be enough force that your finger covering this over here is going to be pushed out of the way, and then the liquid will just start shooting out. Or if you're really, really forceful in holding your finger over here and also pressing this piston down, what'll happen is the sides of this pump or syringe will start cracking, and eventually the liquid will break out. It's kind of like, I know there's like this meme video clip of, what is it? It's a tank full of water some of you will know exactly what I'm talking about. A tank full of water, and it's got like a hole in it, and the water is leaking out, and then somebody slaps a piece of duct tape on it. And then I think that's where the meme clip ends, but the implication is that it's not going to do anything. It's just going to burst and break, and all the water is going to just come flooding out even faster if you try to force it to stay in. But yeah, if you know which meme video clip I'm talking about, that's the one. That's also an illustration of this point. Okay, so apart from that, what else have we mentioned? We've defined ideal fluids. We're just going to assume most of the fluids that we're working with are going to be ideal fluids because that's just what we do in physics. It's just like assuming that air resistance is negligible. It just makes calculations easier, and we'll worry about the more complicated stuff when and if you end up working for NASA, or whatever the equivalent of that is. Worry about it when you get to a level where it actually matters. But right now, we're just learning the basics, so we will keep it basic. Let me see. Next property we want to talk about for matter is density. I've mentioned density here and there. I think I mentioned it a good amount when talking about gravitation stuff, when we were talking about like planets with different densities and volumes compared to other planets, and calculating how, you know, a planet of 2 times the radius of Earth and 1/4 of the density, how does the gravity on the surface of that planet differ from the gravity on the surface of Earth, or whatever. That was one place where density was mentioned. I also mentioned density when we were doing rotational dynamics, specifically when talking about things like center of mass and moment of inertia. I think I mentioned those in passing here and there, and said that stuff was mostly going to be a concern for the Physics C students once we get into the calculus stuff for those students. But yeah, even for algebra-based physics, you do need to understand density. So what is density? Density we define with the Greek letter rho. I know you've seen this before. I'm pretty sure I've used it before. Almost definitely in the gravitation chapter. So RHO is how you would write the name of this Greek letter, rho. And there are different types of density depending on what is being spread out over what. Density just measures how much stuff is packed into a certain amount of space, and that amount of space is measured in terms of length or area or volume. And the thing that's being spread out could be mass, it could be charge, it could be something that doesn't even have a physical meaning. Like there's this concept in statistics called probability density, where you measure how the probability of something happening is spread out over the course of, I don't even know what to call it. Yeah, I'm actually not sure what to call it. Well, we'll worry about it when and if we ever do a statistics course. But yeah, there are different kinds of densities. In our case, the density we will be talking about for this chapter will always be mass volume density. And we're going to assume that the density is uniform. There are uniform densities and non-uniform densities. Uniform versus non-uniform densities. The main difference is just uniform density is density that's spread out evenly. Non-uniform density is when the mass is not spread out evenly. I think we gave the example of, well, we assumed for all of our rigid objects, in rotational dynamics, if I had something like a rod, we assumed that the mass was spread out evenly. So if I cut the rod in half, I would know each piece has exactly half the mass. If I cut it into quarters, each piece would have a quarter of the mass, and so on and so forth. A non-uniform density object would be something that you could say, let's say it has the same total mass, but the mass is spread out differently because maybe, let's say I just draw this diagonal line over here. Let's say that this diagonal line separates two different materials that this rod is made of. Let's say that this material over here is like metal, and this material down here is wood, and this side has more metal than wood on it, so this side would have a higher density, while this side has more wood than metal, so it would have a lower density, but the shape and size of the stick are such that it ends up having the same mass as this one. So that's uniform versus non-uniform density, explained simply, I hope. We're going to assume our fluids in this chapter all have a uniform density. And every time we mention density, even though we're not going to call it mass volume density, that's what it is. That's typically what people would assume when you talk about density. If you're talking about any other type of density, though, you have to actually specify what type of density it is. If you're doing electricity and magnetism next year, then you will be talking about charge density, and you can't just call it density. You have to specifically say charge density. If you just say density, people will assume you're talking about mass. If you want to be even more specific, you have to specify, are you talking about charge volume density, charge surface density, or charge area density is another term for it, or charge length density, charge per unit length density. But in our case, anytime we say the word density, we are specifically referring to mass density, and we are specifically referring to density by volume. Not length, not area, volume. So that is density. Typically, solids have higher density than liquids, and liquids have higher density than gases. I think you can already kind of see this just from the way that the atoms are packed. With solids, a lot of atoms in a very small amount of space. Lots of mass, little volume. A lot of mass divided by a little volume equals a lot of density. Here, a decent amount of mass spread out over a bigger volume. So that's a lower density, and then you've got less mass taking up more space. This will be a rather low density for gases. That's typically going to be the case, but of course there are going to be some solids that actually have lower density than some liquids, and there are going to be some liquids that have lower density than some gases. There are going to be, let me think, what is an example of a good exception? One really high density liquid that is heavier than some solids is mercury, which we will be looking at quite a lot. I actually don't know its density off the top of my head. Hold on. Let me see if it's actually listed in my book. Actually, I need to see if there's like a table of densities in the OpenStax book that I link in the course plan. There should be. Let's see, where can we find it? Ah, yeah, here we go. Let me switch to this screen real quick. Yeah, here we go. So this is on page 472 of the OpenStax book, which is linked at the top of the course plan, and the course plan is linked in the description of this video / stream, depending on when you're watching this. So yeah, we've got the densities of solids. This is in kilograms per cubic meter, which converts or rather in thousands of kilograms per cubic meter, which also directly converts to grams per milliliter. So you've got 2.7 thousand kilograms per cubic meter. Don't forget that this times 10 to the 3 is up here. You've got 2.7, you've got 8.44 for brass, 8.8 for copper. Let's see, do we have mercury? Mercury is 13.6 times 10 to the 3 kilograms per cubic meter. Compare that to water, which is 1 times 10 to the 3 kilograms per cubic meter. Also, it mentions that the water is at 4 degrees Celsius. There is a reason for that, which we will talk about soon. But yeah, mercury is about 13 times heavier per volume than water. If you take two equal-sized containers, one filled with water, the other filled with mercury, the one filled with mercury is heavier, 13.6 times heavier, typically. And then you have air over here, which is actually super light compared to water. It's a little more than 1/1000th of the density of water. So yeah, all these gases, carbon dioxide, carbon monoxide, hydrogen, helium, you're seeing a lot of them have much, much lower density than the liquids. And mercury over here is actually higher density than some of the solids. We see copper has a lower density than mercury, brass, aluminum, even lead. You think of lead as being really, really heavy because of its high density, and even lead is less dense than mercury. Not gold, though. Gold is still the reigning champion over mercury, gold and uranium. And tungsten, it looks like. So yeah, there you go. There's a sampling of materials that hopefully illustrate my point. Now, where did I want to go from here? Let me double check with my notes. They're all really just bullet points. They're not even very detailed notes, but yeah. Oh, right. We wanted to talk about water and just how densities of different materials change. So density is not just some fixed property based solely on the material. Density also depends on conditions like temperature and pressure. Density can depend on temperature and pressure. This is just something you have to know conceptually. You don't have to actually do any calculations. If you want to calculate how the density of something changes based on temperature and pressure, well, there is a bit of that in physics too, but also there's a bit of that in AP chemistry, or really just any chemistry, any proper chemistry course. Temperature, density can depend on temperature. I don't know what I was trying to write there. And pressure. And we haven't really defined pressure, but for now we're just going to go with our colloquial understanding of what pressure is, and we'll define pressure mathematically in a bit. So density can depend on the temperature and pressure of the substance, of the material. That's because, well, temperature, you may have learned way back in like elementary school science that when things heat up, typically they also get longer. Their volume increases. If you heat up a solid, you may have been told that railroad tracks are designed in such a way that they have gaps in between sections of rail. And the reason for that is because in the summer, when it gets hot, that metal will stretch. And if it doesn't have enough room to stretch, and take up this space over here, well, what's going to happen is it's going to stretch against itself. So if I put two pieces of metal right next to each other like this, and then they heat up and they start stretching and they can't stretch against each other, they can't push against each other, well, then they're going to have to move in a different direction. They're going to have to expand in a different direction. So what will happen is they can't go into the ground. They're blocked by the ground, so they have no choice but to go up. And that's when you get this situation where the rail is just going to have, it'll be like broken metal sticking out like this. And yeah, you definitely don't want trains running over rail that looks like this, now do you? So that's why we put gaps in between different sections of railroad rail. But this expansion means if you're not changing the total mass, right, you're not adding or removing from the total amount of material that's there, you're not increasing or decreasing the amount of metal, so the mass isn't changing, but the volume is increasing. That means the density is getting lower. Typically, when things heat up, they expand, which means typically when things heat up, their density decreases. Typically, emphasis on the word typically. Density, typically, emphasis on typically, decreases with increasing temperature. And that's because substances typically increase in volume with increasing temperature. I misspelled temperature there. Temperature. There we go. Temperature, that should be a U, not an A. Density typically decreases with increasing temperature. But water is one of those weird exceptions. So water has this strange behavior that's also actually quite beneficial in some ways. So here's what the volume of water does at different temperatures. So you saw water at 4 degrees Celsius is what it said in that chart earlier. They said water at 4 degrees Celsius. If you were to draw a graph of water's volume versus temperature, 4 degrees Celsius is where water has its lowest volume. That's where the water is packed into the smallest amount of space as humanly possible, and that then just goes up as you decrease the temperature, but also up as you increase the temperature. And it kind of looks like a parabola-shaped graph. So yeah, the volume of water actually increases when it's cooled down. Most substances don't behave this way. Most substances, when you cool them down, the atoms get closer together, the volume decreases. But for water, there's an exception. And the reason for that, if you want to, again, look at that chemistry video I mentioned a few minutes ago that talks about intermolecular forces, water molecules are in their own kind of special category. They're one of the few molecules that have the ability to create this interaction called hydrogen bonding, which is pretty strong bonding. It's not the strongest, but it is the next tier after ionic bonding, which is some pretty strong bonding that you typically find in solids. So it's one tier below that ionic bonding interaction in terms of strength. It's the next category under it. And that hydrogen bonding kind of forces the water molecules, once they get close enough to each other for hydrogen bonding to really hold them together, it forces them, it locks them into this arrangement where they are forced into this hexagon pattern. Water molecules kind of look like this. One oxygen atom connected to two hydrogen atoms. Of course, there isn't anything physically connecting them. They're just connected through, electric attraction. But these water molecules will start attracting neighboring molecules once they are cold enough and slow enough for these interactions to happen without them slipping past each other as effectively anymore. And what you end up getting is they arrange themselves in this sort of hexagon pattern. And making that hexagon shape, I'm not going to draw out the whole shape, but basically the atoms end up making this hexagon shape, which has a lot of empty space right here. A lot of empty space that could have been occupied by more water molecules is not being occupied. So in a way, they're being forced to spread out more once you cool them down enough. And that leads to an increase in volume once you get below that 4 degrees Celsius mark. This leads to the density of ice. It's not that long before the water turns into ice. This leads to the density of ice being lower than the density of water. This leads to the density of ice being lower than the density of water, and that is what allows ice to float to the top. That's what allows ice to float to the top of a body of water during the winter. So you'll have, if you have a frozen lake, there's actually still liquid water underneath that frozen lake, as you all know. And that's because the ice floats to the top. Whereas for a lot of other liquids, the solid form would actually just sink in the liquid form rather than float on top of it. So yeah, that is the weird behavior of water. Water is one of the exceptions to this general trend that you might want to be aware of. As long as you remember that 4 degrees Celsius is the magic number, that's what we will assume for water. At 4 degrees Celsius, water has a density of 1,000 kilograms per cubic meter. At 4 degrees Celsius, water, pure water, has a density of 1,000 kilograms per cubic meter. 1,000 kilograms inside every cubic meter of water. Or 1 gram per milliliter if you prefer. Also equal to 1 gram per milliliter. But that's pure water. What if there's stuff in the water? What about salt water? Would you expect that to have higher density or lower density? Well, salt water or sugar water, or really water with anything dissolved in it, it's not going to see any significant change in its volume. There is actually a change in volume that occurs, but again, it's not significant. So we tend to assume that the volume stays the same. But what you're doing when you dissolve things into the water is you're adding mass. You're adding mass, you're not changing the volume, so density has to go up because the numerator in this equation is going up. If volume stays the same and you, of course, you stir whatever you're dissolving in there so that it's still a uniform density. This is the equation for uniform density after all. I forgot to mention that earlier. We're assuming the mass is evenly spread throughout the entire volume. If you're adding more mass to spread throughout the same volume, then density has to go up. Just plain math. So now I think I've said everything that needs to be said about density. Let me think. Oh, actually, one more thing. There's another concept relating to density. Another concept. Which color do I want here? Let's use this purple lavenderish color. There's also this other concept you might run into here and there called specific gravity. Specific gravity. And specific gravity, you can also call it relative density, is what I've seen some people call it. Relative density is just the ratio of two densities. Typically, it's the ratio of the density of one thing to the density of water. Typically, specific gravity is determined by comparing the density of objects to the density of water at 4 degrees Celsius, typically. But you can actually just measure it relative to some other standard if you don't like using water at 4 degrees as the standard. Water at 4 degrees just happens to be a useful standard because, well, it's an easy density to remember, 1,000 kilograms per cubic meter. By the way, I would commit this to memory. It's not a very hard number to remember. 1,000 kilograms per cubic meter is the density of water. I don't know if the AP exam expects you to memorize this, but I expect you to because, like I said, come on. It's right there. It's so easy to remember. So I would not blame them on the AP exam for expecting you to know that off the top of your head. So specific gravity, let's go ahead and actually just calculate some of the specific gravities. Let's go back to this page that I had up a minute ago. Yeah, let's go back to here and let's see what some of these specific gravities would be. So they've written water in the, again, it's in the thousands of kilograms per cubic meter or grams per milliliter, whatever you prefer. But these are all in the same units. So all I would have to do is, if I wanted the specific gravity of brass, for example, brass over here at 8.44, the specific gravity of brass relative to water is 8.44 divided by 1.00. Specific gravity of brass is 8.44, which is unitless because you're dividing kilograms per cubic meter by kilograms per cubic meter, or grams per milliliter by grams per milliliter, or whatever units you happen to be using here. You should end up with no units when calculating a specific gravity. Specific gravity has its usefulness in, I know they use it in geology, I think, to identify certain types of rocks, if I'm not mistaken, but probably the application that you've heard of is measuring people's weight, specifically to figure out like their fat percentage or something like that. A lot of like the athletic gym guys like to do that. There's this machine where they get dunked in a tank of water. They're held up by a harness and it measures like the shift in their weight, quote unquote. It's not actually their weight changing. We'll talk about that later. And based on that, they can do something a little bit more accurate than just standing on a scale and measuring your height and calculating your BMI. So standing on your scale gives you some information. Taking your height into account and calculating your BMI gives you some more detailed information, and then using that machine, I don't even know what it's called, to figure out like the specific gravity of your body allows them to get a little bit more detailed and compare like what percentage of your body weight is fat versus muscle and bones and stuff. I don't know the details of that. I've never used such a machine, but I know people that are really obsessed with bodybuilding have probably had experience with that type of measurement. So if you have some more insight to offer, then the comment section is available. But that's all I can say about that for now. Let's go ahead and look at... We don't have enough to do any problems yet. And I'm seeing these now. I forgot to mention, if you came across the concepts of tensile stress and shearing stress and bulk stress, volume stress, whatever you want to call it, those are not really for us. I did mention to skip those topics, I believe, in the course plan. And stuff about like material strength and elastic limits. That's stuff that if you plan on doing like engineering, it'll become important, but it's not for the AP exam, at least based on my understanding of the course description. The course description doesn't mention anything about that stuff. So now let's move on to defining the concept of pressure. Let's grab a new sheet and get started on that. Let's talk about pressure. And if you're looking for help online and anybody tries to explain pressure to you by bringing up the topic of tensors or whatever, just run. Don't walk, run, because those people are not trying to help you. Those people are trying to show off that they've taken like higher level college physics courses. You would think if they were actually trying to help, you would think they would realize that they need to be talking on a high school level. But yeah, run for the hills if you hear anybody talking about tensors. Too early for that stuff. You'll learn about tensors if you go far enough into like engineering and physics and math in college. Maybe like third or fourth year. I don't actually know because I never took the course that talks about that stuff. Maybe I'll learn it on my own time later, just for fun, when I actually have the time to learn things just for fun. But pressure. So pressure is a scalar. Pressure is a scalar. Is a scalar. And pressure is defined as the magnitude, whoops, not mg, as the magnitude of force acting perpendicular to a surface divided by the area of that surface, divided by the area. So if I have just a surface, just this square patch of ground, and I have some force acting on it, and let's say that force acts on it at some sort of angle like this, one thing that can be helpful is if you just draw a line perpendicular to the surface and then get the angle between the force and that perpendicular line. And whatever that angle is, you take this force times, I guess it would be the cosine of the angle, and you would just calculate whatever the magnitude of this perpendicular force component is. So this F cosine theta is what you would actually use. So pressure with a capital P is equal to F perpendicular divided by the area of the surface that the force acts on. So up until this point, we've not really been worrying about how the force spreads out over an object that's being pushed or pulled. If I push down on this table with my hand, I'm not just using the full force of my hand at one point on the table. We've been treating it as such, kind of. We haven't really been worrying about it one way or the other, actually. Except, well, I guess we have been treating it as acting at a singular point for things like when we were doing torque calculations, for example, determining the point where the force is being applied and whatever. But actually, it's typically going to be applied at multiple points. You're typically going to have some sort of area of contact if it's some sort of contact force like the normal force. And that force is going to be spread out over the area, whatever area my hand is currently pressing on. The force is going to be spread out over that area. I would say about evenly, although I guess there is technically like an air gap over here between my palm and the paper, so that could make it a little bit uneven. But yeah, pressure helps take that into account. Pressure helps take like the size of the surface of contact into account. And it helps explain things like how with really, really tiny amounts of force, you can break through things. I could, for example, with a really tiny amount of force over here, I could poke a hole through that piece of paper. There you go, I poked a hole through it. I don't know how visible that is to the camera, but hopefully you can see a little bit of something through it. Maybe? No? So I can poke a hole with a really, really tiny amount of force with my pen, but no matter how hard I press my hand down, and I know the full force of my hand is greater than the force that I just poked through the paper with, and yet I can't get this paper to rip. Why? Because in the case of poking the paper with my pen, I'm focusing all that force on a very small amount of area, and the amount of stress that the material of the paper can withstand, the amount of pressure that it can withstand before it caves, is easily exceeded when I just focus all that force on a tiny part of the area. Also, this understanding of the definition of pressure helps us explain things like how a girl in high heels actually exerts more pressure on the ground than an entire elephant, because elephants have really big surface area on their feet, and also they've got 4 feet. Legs, feet, I don't even know. What would it be called? They're not hooves. I guess they're just feet. Okay. I don't know what the official term is, but we'll just go with feet. Elephant feet have a large surface area and they're pretty much flat, versus high heels tend to concentrate a person's weight on a very tiny amount of surface area. So more force is exerted by the high heels than an entire elephant. Surprising, but true. And we might actually have a book problem relating to that at some point. I think I saw one in there. I didn't read them super fully, but I read them just far enough to be able to tell that they'd be good problems to look at. Anyway, what else did I want to say here? Let's see. So, magnitude. It's the magnitude of the force perpendicular to the area. So another thing you could do is you could rearrange this equation and say if you want to calculate the force perpendicular to an area, you can just take the pressure, if you know it, and multiply by that area, and you can calculate how much force that area is experiencing, at least perpendicular to it. We don't know anything about the non-perpendicular part of the force. In cases where you start knowing pressure and area only. But yeah, that's the basics of pressure. So units of pressure, you can figure it out pretty easily over here. If your standard unit of force is the Newton, and your standard unit of area is going to be meters squared, then the units of pressure would be newtons per square meter. Whoops, square meter, not cubic meter. Newtons per square meter will be the standard units for pressure. This is also known as 1 Pascal. This is also known as the Pascal, or PA. The PA does not stand for, what is it? Great, I'm forgetting. Is it? No, wait. Is Pennsylvania PA? I am blanking on it, but I'm pretty sure there's a state that has PA as its abbreviation. But yeah, whatever state that is, that's not what the PA stands for. It's a lowercase a. That's one clue that you have. Uppercase P, lowercase a, named after Blaise Pascal. Named after Blaise Pascal, who I believe was French, if I'm not mistaken. So yeah, that's the standard unit of pressure, but there are other useful units of pressure that you may have heard of. There is the other units of pressure include other units of pressure. If you've done chemistry, you've heard of all of these. Other units of pressure. They include the PSI, which is pounds per square inch. Pounds per square inch. PSI, pounds per square inch. Used by Americans. You see this on your tires. It will typically be written on the tires of your vehicle how much pressure it needs to be filled to. Another unit of pressure that is frequently used is the atmospheric pressure, the ATM. Atmospheric pressure. This is in terms of multiples of the amount of pressure that the air from the atmosphere exerts on the surface of the sea, at sea level. Atmospheric pressure. Where 1 atmospheric pressure is calculated to be equal to 1.01325 times 10 to the 5 pascals, and this is the air pressure exerted by the atmosphere at sea level. It has to specifically be at sea level. This has to be at sea level, because if you are above sea level or below sea level, then the amount of air above your head, the amount of air above that surface at different elevations is going to change, and therefore the total force that that air is exerting downward on that surface is going to be different. At higher elevations, the pressure is going to be lower. At lower elevations, the pressure is going to be higher. And some people might be thinking, well, lower elevations than sea level, wouldn't that just be higher because there's also water? Not necessarily. You can be below sea level and still be on dry land. You know, you could be like in a valley region that's nowhere near any bodies of water, right? So you could be somewhere that's deep but not under the ocean. But yeah, if you're under the surface of water, then there's a separate calculation that you have to do for the water. We'll talk about that later. But yeah, that is the atmospheric pressure. And actually, now that we've defined an atmospheric pressure as 1.01325 times 10 to the 5 pascals, we can say the pound per square inch, 1 psi, 1 pound per square inch, depending on who you ask, it's either 14.69 or 14.70. We'll just go with 14.70 for now. 14.70 atmospheres, if I'm not mistaken. Actually, let me double check. Let me Google this real quick because I'm doubting myself here. PSI to ATMs. No, I think it's the other way around. ATM to PSI. There we go. Yeah, that's what it is. Okay, my bad. See, I knew something was off about it. I should have known. Yeah, 14.7 psi is equivalent to 1 atmospheric pressure. There we go. Another unit of pressure is the bar. Another unit of pressure is the bar. This one is really simple. 1 bar is equal to 10 to the 5 pascals, 10,000 pascals. So you could actually just write 1 atmosphere of pressure is 1.01325 bars, and then you could drop this times 10 to the 5 business. Another couple of units that you might see is HPA and KPA. Hectopascals and kilopascals. Hectopascals and kilopascals. Hecto just means 100. We don't encounter this a lot, but yes, it just means 100. So if you see it somewhere else, now you know, it just means 100. And kilo, we've seen kilo thousands of times, pun intended. A kilo is 1,000. So a hectopascal is 1 hectopascal is equal to 100 pascals, and 1 kilopascal is equal to 1,000. So if you see those, I think you'd be more likely to encounter kilopascals than hectopascals, but that is something you might come across. And then one last unit for pressure. I know, so many units. One last unit for pressure is the millimeter of mercury, or, for those of you who remember it from chemistry, the Torricelli, abbreviated TORR. Millimeters of mercury or torrs. And this one, we'll see an explanation later for where it comes from, but for now, all you need to know is that 760 millimeters of mercury, or 76 centimeters if you prefer, is equal to 1 atmosphere worth of pressure, 1.01325 times 10 to the 5 pascals. So if you remember how to do your dimensional analysis and do all your conversions and all that, then you should be good to go no matter what units of pressure they throw at you. And sometimes you will see problems where you don't even need to convert to standard units to begin with. Sometimes you'll have those types of problems where what you put in is what you get out, in which case you might not need to change anything and you can just start the problem right away without having to do any conversions. But yeah, we'll encounter this actually pretty soon, if I'm not mistaken. Let me see. Yeah, actually, it's our next topic. Let me see with my notes. Is there anything I forgot to mention? Nope, we're heading there. Okay. So then, what does pressure allow us to determine as far as fluids are concerned? Well, pressure allows us to determine where fluids flow. Pressure allows us to determine where fluids flow to and from. So fluids flow from high pressure to low pressure. They flow from high pressure to low pressure, if given the opportunity. So if the fluids are not flowing, then that means the pressure is equal between the two positions where you would have expected them to flow. If fluids are not flowing, then that means that the pressure on both sides of whatever boundary they're supposed to flow through must be the same. So, I lost my train of thought. Hold on. There was something I was going to say here. What was it? Why am I blanking on this? I don't think looking at my notes will help me remember, but we'll try. Something relating to fluid flow that I did not put on my notes. What was it? I feel like it was going to be a chemistry-related comment. Okay, I've got it. So what we're talking about over here is we're talking about net flow. We're talking about net flow. So in reality, on a microscopic level, if you have like a container full of water, if you have a glass of water and you just leave it sitting on a countertop or a table or whatever, and you just leave it there, you don't touch it, you don't disturb it in any way, you would say, just with your naked eye judgment, that the water is sitting still. Well, it's not actually sitting still. The particles in the water are still moving On a microscopic level, you just don't see that movement. But the net movement, the net flow, these water particles are moving somewhat randomly. Some are moving like down and to the left, some are moving down and to the right, some are moving up and to the right, some are moving up and to the left, some are moving straight left and straight right, or straight down or straight up. But overall, there's just as much overall leftward motion of particles as there is rightward, and there's just as much upward motion as there is downward. So the net flow is 0. The net flow is what's 0. So when we're talking about fluids flowing from high pressure to low pressure, we're specifically talking about the net flow. On a microscopic level, these particles are going to be moving all the time. They're going to be sliding past each other all the time. But it's only when you have like some net flow, when there's some overall flow from the left to the right or the top to the bottom or whatever, that's actually visible to the human eye. That is what we see if there is a significant difference in pressure between 2 points within a fluid. Okay, I'm glad I was able to grab that point back before it completely disappeared from my mind. Now then, let's talk about Pascal's principle. Pascal's principle. So Pascal's principle tells us the following. Pascal's principle tells us that let me see, how would I word it? Pascal's principle tells us that fluids in a container must have equal pressures at equal heights. That's one way you could word it. Must have equal pressures at equal heights or depths, depending on how you want to look at it. At equal heights or depths. So typically the picture that they show you in a physics textbook, actually let me see if we have a picture of it in the OpenStax book. We probably do. No, we actually don't. Well, how about that? Okay, I can try and fit this one. Yeah, I don't know how I'm going to get this to fit under my document camera, but they have this here. Let me try and bring the corner of the book around like this. Does that work? It's kind of sideways, but hopefully you can see it. They've got this set of tubes of different shapes, and you see that all of the tubes are open, and they're all, like, the liquid is allowed to flow from the bottom between all of these different tubes, all 4 of these tubes, and yet you notice that all of the tubes, they fill with this, I'm assuming this is just water with blue food coloring, they fill up to the same height. Hopefully that was still easy enough to read despite having to block some of our lighting. So yeah, if I were to, I guess I can attempt to redraw it. I won't draw it as accurately, but this is an experiment that I guess you could do at home if you have something of the right size and shape. I don't know who would have something like this lying around, but if you have this series of tubes of different shapes and sizes, one of them looked like this and had like some sort of bulb, and then another tube, I guess, I don't know, had like some sort of squiggle. I'm not going to be able to draw that really well. Okay, that's my attempt. It's probably not going to be a very good one. Yeah. Gotta work on my 3D drawing skills some more. Had some sort of tube shape, some sort of twisty tube shape like that, and then another one was just like an angled tube like this. And you just start pouring some liquid into here, then all of the liquid eventually pushes up through each of these tubes to the same height. It all pushes up to the same height. And the reason for that is because if one side had more height than the other, then if like one of these tubes had the liquid go to a higher height, if this one, for example, was overfilled by this much, well, this would create some pressure. This would be creating some pressure compared to all of the liquid below it. And all of this liquid over here is supposed to be at the same pressure according to Pascal's principle. So if there's more pressure on top of this part of the tube, on top of this part of the tube isn't the right word. Hold on, I'm struggling with words today. If you have this extra force due to the weight of this extra bit of liquid over here, it's going to create extra pressure on top of this section of this, I guess we'll call it apparatus, that doesn't exist on top of the surface of the liquid over here, or here, or here. The rest of these other three, there's just air on top of the surface of the liquid. So the force over here of this extra bit of liquid is going to create a greater pressure than the pressure from the air on top of these three. And that difference in pressure leads to a net flow. There needs to be some sort of net flow from this high pressure position to these lower pressure positions. So what will happen is over time, these will start to climb up, this will start to go down, and then eventually it will all become even again at some new height, whatever that new height is. Let's say it's that second dotted line I just drew. So yeah, that's Pascal's principle. That's the basics of it. Once a fluid is done flowing around and sloshing around within its container, once it's settled, the pressure at any given height or depth must be the same throughout the entire container. So all points along this line have the same pressure. All points around any line I draw here. If I were to draw a line down here, all points along this line have the same pressure. Now, they might not have the same pressure as all the points along one of those higher lines. At greater depths, actually, there's going to be more pressure than over here, but the pressure is equal for all the points along this line. There's no net flow horizontally at the very least. Also, once it's settled, there's no net flow vertically because whatever this pressure is, as high as it may be, there's going to be just as much pressure on top of it as it's exerting upward, so there's no net upward flow anymore once it's settled. I feel like I could have prepared a better explanation for this one, but I'm going to need to think about it. Maybe next time I'll revisit this and give a more satisfying explanation, because I don't feel satisfied with this. For the time being, I guess we'll have to do something that I don't really like to do, which is just trust that Pascal's principle works. Okay, so now that we have talked about Pascal's principle, how do we actually measure the change in pressure at different depths? This actually might help in convincing us that, despite there being a pressure difference between lower and higher positions within a fluid, the fluid can still be stable. So let's go ahead and take a look at how pressure changes with depth. How pressure changes with depth. Or if you like the fancier terminology, variation of pressure with depth. So let's say we have just a normal container, like a glass full of water, and I'll just model it as a simple cylinder, even though glasses are usually going to have a little bit of a fancier shape than just a straight cylinder. And let's say I've got some water in here, and I want to measure how much pressure there is at a point, say, down here. I want to measure the pressure at this point. What is the pressure at this point? Well, we have the definition of pressure. It's the magnitude of the force perpendicular to the area divided by that area. So over here, I would consider the area to be just the area of a circle, right? There's like a circular slice, there's a circular cross section of this glass of water, and that is the area that I would be using in my calculation. And I need to figure out the amount of force exerted on top of this circle. How much force is being exerted, at least perpendicular, on top of this circle? Well, that force would have to be equivalent to the weight of the water above it. It would have to be equivalent to the weight of the water above here. So how much water is there? Well, if I knew how high the water was above this particular point, so we can call that H. Some people also call it D because it's depth, and honestly, I think I would prefer to call it depth, but I know a lot of textbooks use H, so we'll just go with the textbooks for this one, just to minimize confusion if you're going to be looking at your book later for this. So if I know the height and we can figure out the area, then the volume is going to be the area times the height. The volume of water is going to be the area of this circle times the height. Okay, and then if I want to know the weight of the water, the mg of the water, then I need to know the mass. The mass of the water is equal to what? It's equal to the density times the volume, because density was mass over volume. If you multiply both sides of that equation by volume, then you get density times volume equals mass. So then to get mg, my force perpendicular to this area, is going, well, it's not the weight that's directly being applied here. We're measuring, I guess it would be the normal force that the water above this circle exerts down on this particular circle, right? It would have its weight, mg, acting downward on it, and then it would have, I guess you could call it, some normal force that the water beneath this circle exerts upward on it, and it's going to react to that by exerting an equal amount of force downward. The reaction to mg is going to be the force of gravity that that column of water exerts on the Earth's core. I know you probably are sick of hearing about topics like the force chapter that feel like so long ago, but I need to be particular about that stuff, because if I'm not, then that will lead to easy mistakes, especially on the free response questions where you need to really explain things. Anyway, so the magnitude of this perpendicular force, it's going to be equivalent to mg, even though it's not actually the weight directly applying to the surface of that circle. And that's going to be equal to rho v times g. The m gets replaced with rho v, and you multiply that by g. Be careful with your v's and make sure you don't confuse them with your lowercase v's for velocity, because yes, that is still going to be something in this chapter. We'll see that next stream. So try to make your volume v's, your capital V's, look very clearly like capital V's. Anyway, so that's the force, and if I want to divide it by the area, then I do magnitude of the force divided by the area. Well, in this case, yeah, just don't put an arrowhead above it, and its magnitude of force divided by area is going to be rho times Vg divided by whatever the area of this thing is, pi r squared. It's actually not going to matter. We don't actually have to calculate this area because the volume is equal to the area times the height. Whatever this area is, multiply it by the height. You get rho times A times H times G divided by A. And the areas cancel out, so the area doesn't even matter. And so we're left with rho times H times G. I'm going to rewrite that as rho GH. Rho GH. This is the amount of pressure exerted by a column of fluid sitting a height h above a particular point. And this might look familiar to you. It kind of looks like the mgh that we use for gravitational potential energy. Hold on to that thought. We'll see something next stream that might bring up some of those old memories. We're going to see an equation where basically all your m's get replaced by rho's. But that'll be for next time. So yeah, rho GH, that is the pressure due to this column of fluid sitting above, well, even more fluid at this point. But that's not the whole story, because there's something else exerting pressure above this point. That's right, we have to take into account the atmospheric pressure. And I probably shouldn't be using like a downward arrow here because pressure is a scalar, it doesn't have a direction, but just for intuition's sake, we'll say that this is a quote-unquote downward pressure, but it's really just equal in every direction. The atmospheric pressure also needs to be taken into account. Sometimes it's called PATM, P atmosphere. Sometimes it's called P0, depending on whatever your textbook uses. But But yeah, this is also something we need to take into account. So the actual total pressure above this surface, the actual total pressure at this point is going to be equal to this P atmosphere, or P0, P not rho, P atmosphere plus this rho GH quantity that we just derived. And if this container has a cover blocking off the pressure of the air, well, then in that case it's just rho GH. If there's no air above this thing, if it's a closed, sealed container isolated from the air, then yeah, in those cases you would just remove the atmospheric pressure from this calculation. That's the difference between two different kinds of pressure measurements called the absolute pressure and the gauge pressure. So I guess I'll fit it in here. Absolute versus, actually, you know what? No, I'll do it on the back over here. Let's talk about absolute versus gauge pressure. Absolute pressure versus gauge pressure. And yes, it's pronounced gauge, not gauge. Gauge. Don't you just love the English language? The spelling clearly communicates how it's supposed to be pronounced, right? Right? English is such a mess. But that doesn't mean we should just give up on learning it. Absolute pressure versus gauge pressure. So, what is the difference between these two things? I basically gave it away already. The absolute pressure is taking, everything into account, atmospheric pressure and all that. Gauge pressure is the pressure that your pressure gauge measures. That's kind of why it's called gauge pressure. If you had something like a tire and you stick a gauge to it, if you have something like a tire, here's a car tire. I'll put some lines on it to represent like the tread. And there's going to be like some point over here, it's going to have like a screw cap on it, and you unscrew the cap and you take it off, and then you take your pressure gauge meter thing that looks like this typically, and it usually has like a little thing that sticks out, and the higher the pressure, the more of it that sticks out if you're using like one of those non-digital classic old school analog pressure gauges. Or maybe it'll have like a dial attached to it instead of this thing. Maybe it'll have like a one of those pressure dials with the little needle that moves as the pressure increases or whatever. If you stick this gauge into the little tube opening thing after unscrewing it off of the tire, then what you have is a closed system. All you have is this system is completely isolated. This pressure gauge, when you stick it in, it prevents pressure from the atmosphere from, affecting the pressure inside the tire. All the pressure is going to be between this gauge and the air within the tire, so you would be measuring gauge pressure there. A better illustration of this, a cleaner illustration of something that pretty much serves the same purpose as the tire gauge, is the manometer, or manometer, depending on how you want to pronounce it. The manometer. Those of you who've seen my chemistry videos might remember this thing. So this thing, it could be an open-ended manometer or closed-ended. We'll go with a closed-ended one for now. It'll be this tube that's kind of U-shaped. and usually it has like some sort of liquid or gas container over here connected on one end, and this end could be opened or closed. We'll keep it closed for now. Let's say this is like the tire. Like this is the air in the tire. There's air particles in here. And then over here you attach your little pressure gauge with its little needle that will just start swinging to the right as the pressure increases, and it'll stop at whatever pressure it reads. So this is a closed end manometer. That's basically what you are forming when you stick this tire gauge into a tire. You're basically attaching this piece over here to it, so it's closed on this side and it's already closed on that side, because we're assuming this tire doesn't have any holes in it where atmospheric pressure could influence it. So yeah, the only pressure that's being measured is just the pressure of the air within the tire. That's the only thing here that's pushing against whatever is in this gauge and causing its needle or the little stick that comes out of it to move and give you your pressure measurement. So that's gauge pressure. It's just the pressure of the fluid in the container without the atmospheric pressure. The absolute pressure, on the other hand, if I were to draw another manometer over here, and stick a little pressure gauge onto it over here and wait for it to give me a reading. In this case, you've got pressure from the atmosphere plus pressure from whatever's in here, air, water, some other fluid, whatever the case may be. You've got pressure from the atmosphere on top of pressure from whatever substance is in here. Gives you some sort of net pressure calculation here that this device will just read out for you. So yeah, it's a pretty simple difference between these two things. Absolute pressure just includes the atmospheric pressure with it. So be very, very careful when doing problems. Be very, very careful when reading, and make sure you know what kind of container you are looking at. Is it a closed, rigid container, or is it an open container? And if it's open, is it open on one side or both sides? That can affect things. Because if it's open on both sides, so there's this thing kind of like the manometer, except it could be open on both ends, or open on one end and not the other, or closed on both ends. It's this U-shaped tube, the original YouTube before the internet became widely used. Physicists and chemists were using YouTube before it was cool. Yeah. And you would do something like, you could have like, I don't know, water over here, and then maybe on this side, let me see. Let me think. If I want to mix water and oil, I guess the oil would have to be pushed above the level of the water. So if I were to put something like water and oil over here, let me color this in, let's do orange. That's the closest I have to the color of oil. Maybe I have two different fluids in here, and I want to figure out, how much higher the liquid is on this side compared to this side. So I would have to take into account whether this thing is open on both ends or just open on one end and not the other. In this case, if it's open on both ends, then both ends have atmospheric pressure coming in, but because it's on both sides, you could say it cancels out. And then we could do some sort of calculation here. We could figure out, let's see. We know from Archimedes' principle that the pressure over here must equal the pressure over here. I guess orange isn't the right color for marking that. Let's try a dark blue. That the pressure over here must equal the pressure over here, and similarly the pressure over here must equal the pressure over here. I guess I'm actually doing this as an example problem, aren't I? Okay, let's come up with some numbers. Let's go with density of water, of course, is just going to be 1,000 kilograms per cubic meter, and density of oil, it's going to be lighter than water, so let's make up some number. Different oils are going to have different densities. Let's just say 900. Keep the numbers simple for now. 900 kilograms per cubic meter I think is decent. And let's see what we can do with this. I guess I need to figure out, I need to identify a height over here. Let's say that this over here is, let's say this is, how about 2 centimeters worth of water exists between these two lines. And then the goal, I guess, would be to figure out how high is this column of oil. Okay, yeah, let's do this. So pressure down here has to equal the pressure down here. And all I have to do is I can neglect atmospheric pressure because it's going to cancel out on both sides. Or, you know what, we'll write it just to show that it cancels out. And yeah, pressure above this point must equal pressure above this point. So I'm going to say P0 or P atmosphere plus P water. On the left-hand side equals P0 or P atmosphere plus, it's all oil on the right-hand side, plus P oil on the right-hand side. Now, technically, there is less atmospheric pressure on this side than this side because there's the height of the air is smaller over here than it is on this side. The height of air above this side is less than this side, but that difference is negligible because compared to the densities of water and oil, the density of air, we saw it earlier, it's like almost 1/1000th of the density of water. It's not going to make that big of a difference, so we are actually going to neglect that. It is common practice to neglect that difference. Variation in pressure with depth does apply to air. Like I mentioned earlier, atmospheric pressure from the air does change with elevation, but it has to be like a significant change in elevation. You have to go from, like from the valley to the mountain to notice significant changes in pressure. Well, maybe not that far. Maybe you just have to climb from, say, the first floor of a building to maybe the 3rd floor or higher is when you'd start to notice a significant difference with measuring devices, but physically you're probably going to have to, climb up a mountain before you start feeling the difference and feeling nauseous or just having a little bit of difficulty breathing. But with measuring equipment, yeah, you have to move up or down about, I would give it, what, 10 meters? You know what, actually, maybe we can calculate it later. Maybe later we can just make up a problem and calculate how high we would need to go, how much of a change in elevation we would need to go through to experience a significant change in atmospheric pressure. But now we're going off on tangents. Let's get back to this. Actually, let me write that down on my notes so I don't forget it later. How high or low to go for pressure atmosphere to change significantly. To change significantly. Okay, there we go. I'll deal with that later. Now, where were we? So, yeah, for now, we're going to say that the atmospheric pressure on each side is the same and cancels out. So that just leaves us with the pressure of the water having to cancel out with the pressure of the oil. So we have water is, we said that the gauge pressure for a liquid at a given depth, or for a given height, rather, of a column of liquid is going to be rho GH, so rho water times G times H, or times H water, rather, I'll just call it HW for short, equals rho oil times the same G times H oil. So in fact, we don't even need the G. The G also cancels out over here. So we've got 1,000 times, actually I can just keep this in centimeters. 1,000 times 2 centimeters equals 900 times H oil. If I keep this in centimeters, then the height of the oil must also come out in centimeters. 1,000 times 2 divided by 900 is, I think it's going to be like 1.22. 1,000 times 2 divided by 900. Did I say 1.22? 2.22. At least I was able to recognize that there's a bunch of repeating 2's. My brain is not functioning properly today, apparently. Okay, 2.22 H oil equals 2.22 centimeters. So I guess my drawing is not to scale. I guess for my drawing to be to scale, I would have to use a liquid that's about maybe around half the density of water, is what I'm learning from this. But there you go, there's the U-tube open on both ends. If it was closed on one end and not the other, then the only thing that would change is that the P0s wouldn't cancel out. One side would have a P0, the other one wouldn't, and that would change your calculation by a bit. Let me get a sip of water. Okay, I think now my throat's a bit clear. Or maybe not. Okay, now I feel better. Where do we want to go from here? So we've done Pascal's principle, we've talked about absolute versus gauge pressure, and next order of business is going back and revisiting the barometer, the barometer or barometer. The barometer or barometer, however you want to pronounce it. Tomato, tomato, economics, economics. Hydrocity, hydrosity. Uh-oh, the Sonic fandom is going to come for me now. Okay, so the barometer. The barometer, you can think of it kind of like this U-tube, except it's just a different shape. So the barometer you're going to have a liquid in a container over here, and then you're going to flip over a tube. An evacuated tube is what you would want to use, meaning that all the air has been vacuum sucked out of it, so there's no air in here. And you just stick this tube upside down into this container of liquid, and you wait for the atmospheric pressure to push the liquid up this tube. Again, there is no air in this tube, so there is no pressure above the liquid inside the tube. There is atmospheric pressure above the liquid outside the tube. All of this over here has pressure on it. All of this has pressure on it, but inside the tube, if it's evacuated, then there's no pressure. So what will happen over time is liquid will climb up and up and up through the tube until the height of the liquid is high enough in the tube that it counteracts the pressure above the surface of the liquid. Let's use another color for this. So that the pressure at this point is equal to the pressure at this point, the pressure at this point being the atmospheric pressure. So whatever the height of this liquid reaches inside this pre-evacuated tube, whatever height that reaches, that will allow you, if you know the density of this liquid, that will allow you to measure the atmospheric pressure. This will allow you to measure the atmospheric pressure. So the barometer is a device that can be used to measure atmospheric pressure at different points. And at sea level, we know that that pressure is going to be 1.01325 times 10 to the 5 pascals, as I mentioned over here. And this is equivalent to what again? We also said that 1 atmospheric pressure at sea level is equal to 760 millimeters of mercury. I said we would go back to this, and now we are doing just that. If you choose the liquid mercury for your barometer, then at sea level, the liquid will rise to 760 millimeters. It will rise to 760 millimeters. Well, we had the density of mercury on a chart earlier. It was like 13.6 times 10 to the 3 kilograms. 13.6 times 10 to the 3. So, density of mercury, chemical symbol Hg, is 13.6, or I guess we'll say 13,600 kilograms per cubic meter. 13,600 kilograms per cubic meter. And if I measure how many pascals of pressure 760 millimeters of this stuff exerts, well, then we can do rho of mercury times G times H has to equal what? It's going to be 13,600 times 9.8 times the height is supposed to be 760 millimeters. I'm going to write that as 760 times 10 to the negative 3 if I convert it to meters. So now I've got 13,600 kilograms per cubic meter times 9.8 meters per second squared. That cancels 1 power of meters. Let's see. Let me actually write out the units. So let me multiply the numbers together first. So 13,600 times 9.8 times 760 times 10 to the negative 3. I'm getting it's equal to 101292.8, and then that was kilograms per cubic meter multiplied by meters per second squared. Multiplied by meters per second squared, and multiplied by meters. So that leaves us with, let's see, meters and meters cancel with meters cubed, reducing it to just meters. So you get kilograms per meter second squared. Is that in units of pascals? Well, let's see. 1 Pascal, we said, was a Newton per square meter, and 1 Newton, if we do something like net force equals ma, force in newtons equals mass in kilograms times acceleration in meters per second squared. So a Newton is a kilogram meter per second squared over meters squared. Meters reduce, and yeah, you end up with just kilograms in the numerator and meters and seconds squared in the denominator. So yes, this is indeed in pascals, and would you look at that, it is approximately the 1.01325 that we're supposed to get. I guess 1.013, so we don't have enough significant digits to calculate it precisely, probably because like this 13,600 was a rounded result. But I'm sure if we had more accurate data to begin with, we could get exactly this number. But looks like we were only able to get it up to 3 decimal places. 1.013 times 10 to the 5. So yeah, if I round this, we have roughly that much. Yeah, this would be 1.013 times 10 to the 5 pascals. So there is some truth to it, barring, again, some significant figure sorcery. Sorcery isn't even the right word, it's just the first word that came to mind. There you go. That is why pressure can be measured in millimeters or centimeters of mercury. Well, of course, you could also make a barometer with some other liquids. You probably don't want to do that, though, because of a couple of reasons. One problem with using other liquids is just, I guess, a logistical problem. Liquids of lower density, which is typically what you have, mercury is the densest liquid, I think, known to man so far, unless we can somehow engineer a new one in a lab somewhere. But I'm pretty sure mercury is the king among liquids in terms of density. and everything else is going to be lower in density, which means to create the same exact pressure to match atmospheric pressure, what would it need to do? It would need to go a lot higher in this tube than Mercury does, since it's a lot lighter. So you would need a much longer tube just to be able to actually get a measurement. So yeah, it's impractical for that reason, but also there's another issue, which is volatility. There's another issue, which is volatility. Now, Mercury is still volatile enough to be dangerous, so don't go anywhere near it without, a face mask, and not like your COVID face mask, but like an actual proper mask that's really tightly sealed around your face. Don't go anywhere near liquid mercury without face protection, because mercury can evaporate rather easily, not as easily as water and alcohol, but still some of it does evaporate naturally, just at normal room temperature. If you splash some water on a table and you come back in a few hours, you'll see that the water evaporated, even though you didn't warm it up to the boiling point or anything like that. Evaporation can happen at any temperature. That's what this volatility thing is about. Basically, the idea is, and I explain this better in one of my chemistry videos, so you probably want to go there if you want to learn about this in more depth. But for our purposes, it's good enough to just understand that through the random motion of particles in a liquid, some of them, like I mentioned earlier, might be moving upward. And of course, there's air particles that are also moving around randomly. And sometimes maybe this liquid particle over here wants to jump up, but this air particle collides with it, bounces it back down, and it stays in the liquid form. But eventually, some of these liquid particles do find a path out of the liquid state and just evaporate into the air. So that's what volatility is about. Different liquids are going to have different chances of success at achieving this. I mean, they all do succeed eventually with enough time. It's just how quickly does it happen. So the more volatile a liquid is, the more quickly this happens. And if that happens in this evacuated tube, well then you actually don't just have empty space over here anymore. You actually have some vapor particles of whatever liquid this is. So if this is mercury, you have a couple of mercury gas particles up in here. And now that they're in the form of a gas, they also exert a pressure. They're exerting a downward pressure down over here, but in the gas form, mercury is going to have a different density, a lower one. So that makes the calculation a little bit more awkward if you want to take that into account. You have to figure out how much of my mercury actually evaporated in here, and then you have to figure out how to calculate the amount of pressure that it's exerting on top of the liquid mercury that's above the surface out here. So yeah, it can slightly alter your calculations. The more volatile the liquid, the more off your calculation will be if you just go by the height of the visible liquid column that develops. So water and alcohol, not really good choices compared to mercury, because they are actually more volatile. They evaporate more easily. Anything else on this before I move on to the hydraulic press? Nothing is coming to mind. Oh, well, another thing you can do with the barometer, now that you know how this thing works, is you could take such a device and move to different elevations and see how high the mercury goes. And if you go, up to like the mountains and you use this barometer, you'll notice that the mercury doesn't rise as high, and you can calculate exactly what that atmospheric pressure is, and I don't know, give that information to like the weatherman or something. Anyway, moving on to another application of Pascal's principle, which is the hydraulic press. So the hydraulic press is a simple device that allows you to convert a tiny amount of force into a lot of force and vice versa, depending on your needs. It can be used to reduce force so that you don't accidentally apply too much, and it can also be used to increase force, whatever purpose it is that you need to use it for. So the hydraulic press, here's basically how it works. So you'll have two pistons. They can be disc-shaped, they can be square-shaped, it doesn't really matter. What matters is that there's a difference in their areas. What matters is that there's a difference in their areas. So one is going to be small, the other one's going to be big. And there's going to be some sort of fluid over here. There's going to be some sort of fluid filling the press. So these are going to be like these disc-shaped movable pistons. And then there's going to be some sort of fluid in here. Could be a gas for all we know, but a liquid is better due to its lack of compressibility. Though I guess one reason you might want to use a gas instead of a liquid is so that any leakages are not as messy. So that's something to consider. I don't actually know what is actually used in real hydraulic presses. I would imagine that there would be a case where you would just use air, but I don't know for sure. That might be something to Google later. Anyway, so according to Pascal's principle, if I wanted to measure the pressure at the same height, at the same depth within this liquid, so let's say at this point and at this point along this line, make it a little bit easier to see, that pressure should be the same. That pressure needs to be the same. So if there is some sort of force, if I were to put a block over here, a block of mass m, if I were to stick it on top of here, and I were to stick another mass over here, let's call that big M, then this thing is going to exert a force of mg downward onto this piston. This one is going to exert a downward normal force of big mg down on the bigger piston. And the idea is for these pressures to be the same. You've got, of course, the height of the liquid. I guess I didn't draw it even, but the height of the liquid is approximately equal. So we'll say that the pressure on the left has to equal the pressure on the right. So we'll say pressure of little m plus pressure of liquid. So it'll be rho gh of whatever this liquid is on the left-hand side equals pressure of the bigger mass plus rho GH of the liquid on the right-hand side. We'll say these are equal, or at least close enough to equal. Once these pistons start moving, one will go down, the other one will go up, so there will actually be a difference in the liquid heights, but we're going to treat that difference as being negligible. We're going to treat that difference as being negligible. So that just leaves us with the pressure due to the small mass equals the pressure due to the large mass. So that's going to be the force of the small mass, mg, divided by the area of the small piston equals the force of the large mass divided by the area of the large piston. Or another way we could write this is force small over area small equals force large over area large. I can just rearrange this equation however I want. If I wanted to figure out how the large force compares to the small one, all I would have to do is multiply by the area of the large piston and get the force of the large block is equal to area of the large piston over area of the small piston times the force of the small block. So basically what this is saying is if I were to exert some force downward on the small piston, it would be multiplied by a factor of the area of the large piston over the area of the small piston. So if the large piston was 10 times the area of the small one, then whatever force I exert on the small side, 10 times as much force would be supported on the large side. And if there is something 10 times as heavy over here, well then there you go. I now can lift it with just 1/10 of its weight in force. So yeah, hydraulic press, very useful application for lifting heavy objects. Another application for the hydraulic press is brakes, like in cars for stopping wheels. I actually saw a problem that I would like to do where you have to decrease the input force in order to pump the brakes. But before I look at that, is there anything else I need to cover before we start doing some problems? Well, we've got one last topic here for today, which is the buoyant force. You know what? Yeah, let's cover the buoyant force, and then we'll spend the rest of the time just doing straight problems. Yeah, I think that's what I will do. Before I talk about buoyant force, was there anything else here that needed covering? We've talked about the hydraulic press, we've talked about pretty much everything involving Pascal's principle now. Yeah, let's go ahead and talk about a new kind of force, the buoyant force. Let's grab a new sheet and introduce the buoyant force. Let me grab another color here. What color do I want to use? I don't think I've used this in a bit. All right, Archimedes' principle and the buoyant force. Archimedes' principle and the buoyant force. Perhaps you have heard that things weigh less underwater. Not true. Not true. Objects do not weigh less underwater. That's what the non-physicist believes. Objects do not weigh less underwater. Rather, submerged objects experience an upward force. Submerged objects experience an upward force from the fluid in which they find themselves submerged. Submerged objects experience an upward force from the fluid in which they are submerged or immersed, whatever term you want to use, from the fluid in which they are submerged. Where does this force come from? Well, let's say we have some container containing some fluid. You can assume it's water for all I care. Just some fluid, and we'll go with a liquid for now, although the buoyant force does also apply with gases. And you go ahead and put something in here. Let's say a person decides to dive in here, go in for a swim. Let's say we're looking at a cross-section of a swimming pool. And I guess the person is cube-shaped for our example because physics. And you, if this person is you, if you are in the position of this block, you feel lighter under the water. It's not because you weigh less underwater. It's because there's a difference in the pressure above and below you. There's a force of pressure below, or not a force of pressure, rather. There's a force of pressure that's experienced from below you that is higher than the pressure you experience from above. And we can neglect atmospheric pressure here. You know what? I will include it. I will include it just to show that it doesn't matter. And this difference in pressure is going to explain why there's some sort of upward force on you that makes it feel as if you weigh less. So there's going to be some pressure down here. We'll call it P2. And there's going to be a pressure up here. We'll call it P1. And of course, you've also got the atmospheric pressure, so I guess we'll call this P1 plus P0, and we'll call this P2 plus P0. Okay, well, what is P1? P1 is just going to be the density of water times G times whatever this depth is. We'll call it H1. And then P2, we'll say that this is at depth H2. P2 is going to be rho times G times rho times G times H2. And if we calculate the force due to these pressures, there's going to be a force below and a force above. Force 2 is going to be the total force on the bottom, so I guess P2 plus P0, times the area that that pressure is being exerted on, right? This is just a rearrangement of pressure equals force over area. We did this before. Multiply both sides by area, and you get force equals pressure times area. That's all I'm doing here. Just taking the pressure beneath the object times the area, That'll be F2. And then F1 will be the pressure above the object. That will be P1 plus P0 times, it should be the same amount of area for a cube. It should be the same amount of area. Okay, so if I calculate the difference between these two forces, and I also account for the weight of the object. Let's say this object has a mass of m, and I draw a force diagram for the object, so I'll draw just a cross-section of it over here. It'll have a force mg acting downward on it, and it will have a force upward of P0 plus P1a acting upward on it, and acting downward will be a force of P0 plus P2a is acting upward, and P0 plus P1 times a is acting downward on it. Okay, so then this difference between these two, I can just combine these two into a single force. I can just redraw this. I can just redraw this diagram with a single force acting up on the object, which is going to be P0 plus P2 times a minus P0 plus P1 times a. That's going to be, if you subtract, the P0s are going to cancel out, and you're just going to get P2 minus P1, P2 minus P1 times a for this force. P2 minus P1 is rho GH2 minus rho GH1. It's going to be rho GH2 minus H1 times A. Okay, H2 minus H1. What is that? H2 minus H1 is this over here. It's the height of the object. We'll call it H object, H-O-B-J. So it's rho G times H object times A. But wait, it gets better than that. The height of the object times the area of its base. What is that equal to? That's equal to the volume. That is equal to the volume. So this is actually rho times G times the volume of the submerged object. It's actually not the volume of the object necessarily. It's not necessarily the volume of the object. We're just looking at a simple case here where the entire object is under the liquid. We will have cases where the object is only partly submerged, like a block of wood where part of it is under the water and part of it floats above the water, for example. In which case you would just use, well, if I were to draw that, so let's say you have like a block of wood where only part of it is under the water. Okay, then you've got your P2 is over here and your P1 is up here. And so your force would be, once you subtract P2 and P1 from each other, once you do P2 minus P1 over here, then the difference you would get is the height of the object that's actually submerged, just the part of its height that's actually under the water. So rather than thinking of it as the volume of the object, you should think of it as the volume submerged. You should think of it as the volume submerged. The volume of whatever amount of the object, whatever volume of the object is actually under the fluid, and none of what's over it. So this is the buoyant force. This right here is equal to this upward force is F buoyant. You can call it FB for short. I guess I would call it F with a capital B is what I would call it. This is buoyant force. So this, if it's equal to mg, then the object just stays suspended in the liquid. If it's less than mg, then the object will sink down just slower than it would if the only force acting on it was gravity. So you feel lighter. It's not because you're actually lighter, it's just because you have enough upward force on you to reduce your acceleration. You don't fall as quickly. And of course, if the buoyant force is greater than mg, then what's eventually going to happen is this thing will float up and rise, and some of it will end up rising above the surface, and it will keep rising above the surface until the amount below the surface is just enough to where the buoyant force, now reduced because there's less of the object under the water, is now equal to the weight. So if you stick something under water or under really any fluid, and the buoyant force on it is greater than the object's weight, that is what will eventually happen. The object will float up until just enough of it is submerged to where the buoyant force is exactly equal to the weight. Now, technically, we are also supposed to consider, if the object is partially submerged, technically we're also supposed to consider a second buoyant force. There's going to be one buoyant force due to water for the part submerged in water over here, but there's going to be a second buoyant force due to the air, because air is also a fluid. Air is also a fluid that can exert a buoyant force on an object. But the density of air is way, way, way lower than water, so the effect of it is usually negligible. I'm just reminding you that air can exert a buoyant force because you might get a problem where they tell you, oh, students do an experiment where they try to weigh a bunch of wooden blocks by putting them in, containers of water, and the containers don't have enough water to fully make the blocks float. Like, they could do some sort of experimental design and analysis question where they tell you, there's like these buckets and they have a little bit of water in them, and then you have blocks of different sizes, wooden blocks of different sizes that they stick in there, and you do some calculations, you measure the water level, and you use that to try and figure out, and of course you put it like on top of a scale, and you read like the scale reading, right? There'll be like a scale with some information, whatever it is in grams, kilograms, whatever, and maybe some buttons over here that you can press. And they might give you something like, they tried to measure the height that the water rose to after the blocks were immersed in the water, and then they read the scale reading, and after subtracting the weight of the water in the container, they determined the masses of the blocks, and then part B or part C of the question will be something like, oh, the students were told by their teacher that actually their measurements were an underestimate by some tiny amount, or an overestimate by some tiny amount. Explain this discrepancy. And I won't tell you which is which, but the discrepancy could be, instead of just dismissing it as an error in measuring the height of the water, the discrepancy could be I won't tell you in which case, whether it's the overestimate or the underestimate. I'll leave you to figure that out on your own. The discrepancy could be that they neglected to take into account the buoyant force due to the air. That could be the discrepancy in one of the cases. In the other case, the discrepancy would be what? The discrepancy would be in the density that they choose for the water, because the density of water, we use 1,000 kilograms per cubic meter, but that's for water at 4 degrees Celsius. This experiment was probably done at room temperature, which is somewhere around like 20 to 25 degrees Celsius, depending on who you ask. I think chemistry uses 25 while physics uses 20. At least that's what I've typically noticed, but if there's like an officially agreed upon number, I don't know it. I'm just going by the numbers that I typically see in example problems. So yeah, buoyant force due to air, typically negligible, but you might see a situation or two where it is not. So you have been warned. So rho times g times v. I actually want to rewrite this as you typically see it in textbooks written as force buoyant equals, they write the rho first and then the v and then the g. And again, this v is only the part of the volume that is submerged if the object is not fully submerged. So there you go, new type of force, the final type of force for AP Physics 1. So what does Archimedes' principle say then? Because we just did the math, but what does Archimedes' principle say? Well, it basically says what this equation says. It says that well, actually, its wording is a little bit different. Archimedes' principle says that an object submerged in a liquid will experience an upward force proportional to the liquid displaced. Liquid displaced. What does that even mean? Well, when you put, say, I don't know, a 10 cubic centimeter sized block and dunk it into water, what's going to happen? Well, 10 cubic centimeters of water are going to have to move out of the way, right? If you're going to stick a block of a certain volume into a container that's already full of water or whatever fluid happens to be in there, then that volume of fluid needs to go somewhere. It can't go sideways. It can't, if there's a hole, maybe it can go through a hole in the container, but assuming there are no holes in the container, it can't go sideways, it can't go down. All it can do is go up. It'll get displaced. So that's what it's talking about there. If you see that in your textbook, if you see that if you see the written version of Archimedes' principle, actually, I have it right here. I just happened to be open on the right page for it. How about that? It says, any object completely or partially submerged in a fluid is buoyed up by a force with magnitude equal to the weight of the fluid displaced by the object. Oh, that reminds me. The other thing is, this is the density of the fluid. This is the density of the fluid, not the density of the object. Density of the fluid. If it was the density of the object, well then density of the object times volume of the object equal times g. That's just the weight of the object. That's not a new force. If the buoyant force is always equal to the weight of the object, then that would lead you to the false conclusion that all objects float. That can't be the case. So yeah, this is the density of the fluid. And this actually allows you to determine, just by looking at density, whether or not the buoyant force will be enough to make an object float or sink. If the density of the fluid is greater than the density of the object, then rho fluid times Vg is going to be greater than rho object times Vg, which means buoyant force is going to be greater than the weight of the object will float. And of course, the reverse is true. If the density of the fluid is lower than the density of the object, then rho fluid times Vg is going to be less than rho object times Vg, which means the object will overall still sink, albeit slower than it would in air. All right, now that we have that taken care of, let's go ahead and look at some problems. And that'll be the rest of this stream. What is that? Some random piece of string popped out of this book. All right, to the trash it goes. Now, let's have a look and see what kinds of problems we can do. Some of them are going to be really classic and straightforward, but some of them might require a bit of head scratching. Can't even pick up my pens properly. Let's go ahead and just flip over to a blank side and start fresh. Okay, so this one I believe is just going to be a classic. So it's just a 50-kilogram ballet dancer stands on her toes during a performance with 4 square inches or 26 square centimeters in contact with the floor. What is the pressure exerted by the floor over the area of contact if the dancer is stationary and if the dancer is leaping upwards with an acceleration of 4 meters per second squared? As simple as it is, what I like about this problem and what I appreciate about it is that it actually makes you think about that thing I was talking about earlier, that objects do not apply their weight onto things below them. They apply a normal force equivalent to their weight onto what's below them, typically. But here we're going to see another case. So 50 kilograms is the mass. And then the surface area, I'm guessing that's taking both feet into account, is 26 square centimeters. Area is 26 centimeters squared in contact with the floor. And then we've got case A, stationary. Case B, we've got acceleration equals 4 meters per second squared upward. And what we need to do is calculate the pressure. What we need to do is calculate the pressure in both cases. What is P stationary? And what is P, I guess we'll just call it P up. Okay, so mass is 50 kilograms. We'll just draw a block to represent the person. 50 kilograms is the mass. We have a normal force upward and a gravitational force downward equal to 50 times G, which is about 490, 50 times 5 times 9, yeah, 490. Okay, those are the forces on the ballet dancer. What about the force on the floor? The force on the floor would just be the reaction to the normal force. So force on the floor, I'll draw it in a different color. This is what's exerting pressure on the floor. This normal force is the force that the ballet dancer exerts on the floor. This is the force in question. Okay, so if the ballet dancer is stationary, then the acceleration is 0, normal force and gravitational force need to cancel out, in which case the normal force is equal to 490 upward on the dancer, and that means it's also 490 downward on the floor. So P stationary, I'll just call it P stat for short, is equal to force is 490 divided by area is, how do we convert 26 square centimeters into square meters? Let's do it over here. 26 centimeters squared. Well, 1 centimeter is equal to 0.01 in meters. And if I want to cancel centimeters twice, then I would just multiply by this twice. So I'll square that. And that just means multiply it by 0.01 twice and divide by 1 twice. Dividing by 1 doesn't change anything except for canceling the centimeters. And 26 times 0.01 squared is let's see, that's going to be 4 decimal places, so 0.26 square meters. Wait, is that right? No, 0.0026. I counted wrong. I knew something was off about that. 0.0026 square meters. There we go. So dividing by 0.0026, that's easy enough, so I'll go ahead and plug it in. That's going to be 188,461.5385 pascals. I'll just say it's about 188.5 kilopascals, 188.5 thousand pascals, 188.5 kilopascals. Okay, what about the pressure exerted when she accelerates upward? Well, in that case, the acceleration needs to be 4 meters per second squared upward. So what I would have to do is say net force equals MA equals 50 times 4 upward equals forces up minus forces down, normal force minus 490. Add 490 to both sides. 490 plus 200 would be 690. So the normal force is 690 this time. That's also the force that she exerts on the floor. So 690 divided by 0.0026, which is equal to 690 divided by 0.0026 is going to be 265.384 thousand pascals. So 265 I'll just round it to 265.4 kilopascals. And there we go. Simple problem, but it's very easy to mess up if you mess up on your concepts. If you're holding on to old misconceptions like the idea that weight is something that can be exerted onto a surface, that's not exactly the truth. I know we've seen a lot of situations where the force that one object exerts on another object beneath it is equivalent to its weight, but that doesn't mean that it's the weight itself that's being applied. It's typically the normal force. Or I guess I could see a scenario where it's some sort of tension force instead. Okay, next one says the 4 tires of an automobile are inflated to a gauge pressure of 2 × 10⁵ pascals. So 200,000 pascals. Each tire has an area of 0.024 square meters. Emphasis on each tire. There are 4 tires, so we need to multiply that by 4. Determine the weight of the automobile. Determine the weight of the automobile. So pressure for a single tire is equal to 2.0 × 10⁵ pascals. 2.0 × 10⁵ pascals, or newtons per square meter. Each tire has an area of 0.024. So area for a single tire is 0.024 square meters in contact with the ground. Determine the weight of the automobile. Well, whatever force the tires exert on the ground, they will be exerting some sort of normal force on the ground, and that's going to be equal to the normal force that the ground exerts up on the vehicle. So whatever that normal force is, it needs to counteract the weight of the vehicle. If we were to draw a diagram for this, there's going to be the weight of the vehicle, mg, and there's going to be a normal force. And of course, through its tires, the car is going to exert an equal amount of normal force onto the ground. So that's what we're trying to calculate. Now, does it make sense to use the gauge pressure? They did say that this was the gauge pressure in the tires. Does it make sense to use that, or do we need to recalculate the atmospheric pressure? Or not the atmospheric pressure, but rather the absolute pressure, which would require us to include the atmospheric pressure. Well, the tires should be closed off to the outside world. They should be isolated, so the pressure inside of them should just be the pressure of the air inside of them without any of the pressure from the air outside in the atmosphere. So yes, using the gauge pressure directly should be fine here. But it is good to get into the habit of asking yourself that question anytime gauge pressure is mentioned. Just, make a mental note that you should consider whether or not you need to use gauge versus absolute pressure. Okay, so we've got 4 tires. We can say force per tire is just going to be the pressure per tire times the area of a tire is 2 × 10⁵ multiplied by 0.024 equals what? 2 × 10⁵ times 0.024 is 4,800. It's 4,800 newtons. And that's per tire. That's per tire. So the total normal force would be 4 times the force of a single tire. 4 times 4,800 that's going to be 19,200 newtons. Sounds reasonable for a car. 19,200 newtons. That would have to cancel out with mg since there is no vertical acceleration for the car. At least cars shouldn't be vertically accelerating on the ground. That would mean something very wrong is happening. So if 19,200 is going to be canceling out with mg, then divide by g, and the mass of the car is what? Dividing by 9.8, the mass of the car is 1,959 kilograms. That does sound about right. Somewhere around 2,000 kilograms is the mass of a typical automobile. So I'm getting about 1959.2 kilograms. That does seem reasonable. All right. Do we want to do this one? No, I think we've done enough examples with this variation in depth thing. Okay, we'll leave that one. Actually, wait, did we do an example with a closed container, though? I don't know if we did. We'll skip it. This person leaning in their chair. Nah, that's basically like the ballet problem. Let's see, if 1 cubic meter of concrete weighs 5 times 10 to the 4 newtons, what is the height of the tallest cylindrical concrete pillar that will not collapse under its own weight? The compression strength of concrete, the maximum pressure that can be exerted on the base of the structure, is 1.7 times 10 to the 7 pascals. Okay, this one shouldn't be too bad. You could probably common sense your way through this one, as long as you knew your units. So 1 cubic meter of concrete is 5 times 10 to the 4 newtons. So 1 cubic meter of concrete. 1 cubic meter of concrete weighs 5 times 10 to the 4, so 50,000 newtons. And it's saying the maximum pressure that can be exerted on the base of the structure is 1.7 times 10 to the 7 pascals. Max pressure at base is 1.7 times 10 to the 7 pascals. And it's asking what is the height of the tallest cylindrical concrete pillar that will not collapse under its own weight. In fact, it does not matter if the shape is cylindrical or some sort of like rectangular prism or triangular prism or whatever. All that matters is height. All that matters is height. But basically you would treat this column of concrete the same way we treated a column of liquid earlier when we were doing the rho GH thing. So we are looking for something where the pressure down at the bottom, where rho GH is equal to 1.7 times 10 to the 7 pascals. And to do that, we need rho. Well, actually, we probably don't. Let me see. So we're already given the weight. We're already given mg. We're already given mg and then over cubic meters. So actually, rho g is equal to mg over volume, right? Mass over volume, that's your rho. So mg is 50,000 over the volume is 1 cubic meter. So yeah, there you go. We've already got the rho g, and multiply that by h, and that's supposed to be 1.7 times 10 to the 7. So 1.7 times 10 to the 7 is equal to 50,000 times h. Divide both sides by 50,000. 1.7. Well, hold on. So I can just do, this was 5 times 10 to the 4. So I'll just cancel 10 to the 4, and that's 1.7 times 10 to the 3 divided by 5. 1.7 times 10 to the 3, that's 1,700 divided by 5, which is 3,400 divided by 10, which is 340. There we go. No calculator needed. 340 meters is what I should get, and you get that if you make sure that all of your units are standard units, which they are, right? Cubic meter, newtons, pascals, yes, all of those are standard units. Let's go ahead and look at the next one. No, that's not for us. A collapsible plastic bag contains a glucose solution if the average gauge pressure in the vein is 1.33 times 10 to the 3 pascals. What must be the minimum height h of the bag in order to infuse glucose into the vein? And they're referring to a drawing. So they have a drawing of one of those bags that you see in the hospital, one of those drip feed bags that they plug into your veins, if you're a patient at least. So yeah, they've got a drawing with, here's one of those bags, and it's got whatever fluid is in there. Apparently this is a glucose solution, so it's just sugar water, and then there's a tube, and then it's sticking inside somebody's arm. I'll just draw like bubble arms, and yeah, you've just got that stuck in somebody's vein. So yeah, it says if the average gauge pressure in the vein is 1.33 times 10 to the 3 pascals. So P vein equals 1.33 times 10 to the 3 pascals. What must be the minimum height h of the bag in order to infuse glucose into the vein? Assume that the specific gravity of the solution is 1.02. Assume that the specific gravity of the solution is 1.02. That means density of the solution over density of water at 4 degrees Celsius. That ratio is 1.02. Okay, so this thing has to be raised a certain height above the arm in order for it to exert enough pressure to actually inject this liquid into the blood vessel. That's basically it. So then the pressure needs to be at least equal to the pressure that's already in the blood vessel that's pushing back against it. You need to overcome this pressure. So at what height does it need to be raised for that to happen is the question. We can do pressure that the solution must have is equal to the density of the solution times G times H. The pressure that the solution must have is at least 1.33 times 10 to the 3. So 1.33 times 10 to the 3 equals the density of the solution. Well, the density of water is 1,000 kilograms per cubic meter. So if you multiply that into the 1.02, then you get 1,020 kilograms per cubic meter times G is 9.8 times, we're about to find out what H is. Okay, 1.33 divided by 1.02. Yes, I'm just pre-canceling this 10 to the 3 on each of these, dividing each by 1,000. And then also divide by 9.8. That gives me 0.133 meters. H has to be 0.133 meters, or 13.3 centimeters above the height of the arm at minimum. 13.3 centimeters is not that bad. That's doable without the need for too much equipment. It'll just be hanging on one of those, you've seen them before, those little rack things that just hold the IV bags, and they have wheels so the patient can move around in the hospital and drag it around with them if they want to. All right, next we have a very powerful vacuum cleaner has a hose 2.86 centimeters in diameter with no nozzle on the hose. What is the weight of the heaviest brick it can lift? What is the weight of the heaviest brick it can lift? Okay, so for this we actually need to understand something about how vacuums work. So a vacuum is supposed to push all the air out of itself so that all that's left inside the tubes of the vacuum is, well, a vacuum, empty space, no particles, not even air. So you can think of the vacuum hose as this tube with no air in it, and there's going to be this, I guess, block that we're trying to lift. Is that what it said? What is the weight of the heaviest brick it can lift? Okay, so it's a brick. It's trying to lift a brick. So the idea here is that there will be pressure underneath the brick from, well, the atmosphere, and it's not balanced out by air pressure in the hose because there is no air in the hose. So it's pressure atmosphere multiplied by area to give you the force, minus no pressure on this side. So this force over here would cancel out with the weight of the brick, would cancel out with the force mg, and yeah, we need to figure out what that is. So pressure atmosphere times what is this area? They said it had a diameter, the hose had a diameter of 2.86 centimeters. So that means the radius is 1.43 centimeters, which means it's also 0.0143 in meters, and then area would be pi r squared, would be pi times 0.0143 squared. If I go ahead and multiply that out, pi times 0.0143 squared equals 0.0006424424. I'll just switch to scientific mode here and have it convert it to me, or convert it for me. That's 6.424 times 10 to the negative 4. 6.424 times 10 to the negative 4 square meters. Okay. And so atmospheric pressure times that area. If I do 1.01325, I'll just do 1.013, given what we got earlier. I think it's probably safer to just round to 3 decimal places. 1.013 times 10 to the 5 pascals for atmospheric pressure times 6.424 times 10 to the negative 4. Well, 10 to the negative 4 and 10 to the 5 reduced to just a 10. And then 1.013 times 10 times 6.424. So 10.13 times 6.424 is 65.075. 65.075 newtons. That is the force due to the atmosphere. This is, by the way, this is really just a buoyant force, if you think about it. This is a buoyant force where the brick is submerged in air. And then, let me see, the question was, what is the weight of the heaviest brick it can lift? So what is the mg? We don't need to divide by g to solve for m, we just need the weight. So yeah, it will just cancel out with whatever the weight of this brick is, which means the weight of the brick is 65.075 newtons. We are done. At least we're done with part A. Part B says a very powerful octopus uses one sucker of diameter 2.86 centimeters, so same as the vacuum hose, on each of the 2 shells of a clam in an attempt to pull the shells apart. Find the greatest force the octopus can exert in salt water 32.3 meters deep. Salt water, not regular water, so we have to look up the density of salt water. And actually, let me look for it. I don't remember seeing that in here. Let's see. Ice, aluminum, iron, copper, silver, lead, gold, platinum, uranium, water, glycerin, ethyl alcohol, benzene, mercury, air, oxygen, hydrogen, and helium. Yeah, it does not have salt water. But I know I read it somewhere. Maybe it was in another problem. I mean, we can always just Google it and just go with a number from Google. We don't have to use whatever number the book intended. The point of this is to just be an exercise. Oh, here's one. Yeah. Here's a problem that mentions the density of ice is that number and that of seawater is 1,030 kilograms per cubic meter. So I will use that. I will use that for the density of salt water. And we probably want to start that on a new page. This is already done. Let's grab a new sheet. So the second part of this problem, it's basically the same principle, really, but density of seawater we'll go with 1,030 kilograms per cubic meter. Of course, it depends on, which oceans you're looking at. Some are saltier than others. If this was the Dead Sea, it would definitely be way more than 1,030. The Dead Sea is the saltiest body of water on Earth, I believe. Anyway, reading the problem again, so it said, very powerful octopus uses one sucker of diameter 2.86 centimeters on each of the two shells of a clam, so we need to remember to multiply by 2. In an attempt to pull the shells apart, find the greatest force the octopus can exert in salt water 32.3 meters deep. Height, or rather depth, is 32.3 meters. Okay, so this is gonna have 2 different twists in it. The first twist, of course, is the fact that it's using 2 times the force. That's easy to miss. But the second twist is is that you have to make sure to account for the air above the sea. So there's your sea level, there's some atmospheric pressure up here, and then at a depth of 32.3 meters from the surface is where this octopus is. I guess I can attempt to draw an octopus. One, two, three, four, five, six, 7, 8. There you go. There's your octopus. I don't think there's enough space to give him a face, but we'll try. There we go. Kind of looks more like a ghost, but that's the best we've got. Now, the area of each sucker was just the same as that of the hose. It's the same diameter and everything, so 6.424 times 10 to the negative 4. 6.424 times 10 to the negative 4 again. And that's in square meters. And yeah, otherwise it's basically the same problem. We just need to figure out what is the pressure at this depth, the absolute pressure. So we're going to do 32.3, that's, or let's see, so pressure is going to be atmospheric pressure, P0, plus rho GH equals 1.013 times 10 to the 5 plus 1030 times 9.8 times 32.3. Let's see what that gets us. 1.013 times 10 to the 5 plus 1030 times 9.8 times 32.3 equals about 4.273 times 10 to the 5 equals about 4.273 times 10 to the 5 pascals. And now that you have that pressure at that depth, it's just like with the vacuum hose. You can assume that the octopus has a way of just completely emptying the inside of its what were they called, suckers, and that leaves you with a vacuum of no pressure on one side and then just this external pressure on the other side. This external pressure will when you multiply it by the area of each sucker, will give you the amount of force that is being exerted on the clam. Multiply that by 2, and that should be it. So 4.273 times 10 to the 5 multiplied by 6.424 times 10 to the negative 4. 4.273 times 10 to the 5 multiplied by 6.424 times 10 to the negative 4 is that number, and then multiply it by 2. And the total force that the octopus is exerting is 5.48995 times 10 to the 2. I'll just write that in regular notation. 548.995. That'll be about 549. 549 newtons of force. That's surprisingly low. Yet at the same time, it's surprisingly low because of all this pressure that you have at that depth. I would have expected it to be higher, but at the same time, I would have expected the octopus to not be that strong. So it's surprising in some ways and unsurprising in other ways. Interesting. Well, that's that problem taken care of. Oh, this one. I knew I was forgetting something. There was something I forgot to talk about. But fortunately, this problem will give us the opportunity to discuss it. So it says, for the cellar of a new house, a hole is dug in the ground with vertical sides going down 2.4 meters. A concrete foundation wall is built all the way across the 9.6 meter width of the excavation. The foundation wall is 0.183 meters away from the front of the cellar hole. During a rainstorm, drainage from the street fills up the space in front of the concrete wall, but not the cellar behind the wall. The water does not soak into the clay soil. Find the force the water exerts on the foundation wall. For comparison, the weight of the water is 2.4 meters by 9.6 meters by 0.183 meters by 1,000 kilograms per cubic meter by 9.8 meters per second squared equals 41.3 kilonewtons. 41.3 thousand newtons. Well, the good news is that they actually gave you like the dimensions over here, because I can see some people not being able to follow, myself included, what they were trying to describe with the cellar of the new house. So it's good that they gave that, because that actually helps illustrate the picture that we're looking at. So the idea is they have this house. So there's a house over here. And then under the house, there's going to be, underground, they dig like this thin wall. Well, maybe it's not thin, but for our purposes, we might as well treat it as being thin. They dig up enough to create this wall under the house so that water doesn't come in under the house and, turn all the dirt under the house into soft, mushy dirt, and then you'd have the house sinking, and yeah, that's no good. So they dig under here and they build up this wall underground. And what this wall does, it's dug 2.4 meters down, so this is 2.4 meters. And then it is 9.6 meters wide. It's 9.6 meters wide. And they said the foundation wall is 0.183 meters away from the front of the cellar hole. So basically they're saying, like, over here there's 0.183, definitely not drawn to scale, 0.183 meters worth of, I guess, length that the water can occupy. So yeah, 0.183 here as well. So there's going to be like this, I'll try and draw it to the best of my ability. Something like that. This is where the water will build up, and then I guess I can color it in. Let's use a light color. Let's use orange. I know orange water is probably not what we want to look at, but this will keep it readable. So yeah, water fills up this volume. This much water gets in there. And then it says, find the force the water exerts on the foundation wall. Find the force that's exerted on this wall that they've built. The wall is just here, and then I don't know what's on this other side. I guess there's all this dirt to the right, so the water can't go there, so the only water that can gather is just this amount over here. So, yeah, find the force the water exerts on the foundation wall, and it says, for comparison, the weight of the water is 41.3 kilonewtons. Okay, so for this problem, we would need to calculate the average pressure of the water. The water is going to have different pressures at different heights. It's going to be the lowest pressure at, well, near the surface, and its highest pressure is going to be at the bottom. And the fortunate thing for us is that even though the pressure changes with depth, it changes linearly. And when the change is linear, the rate of that change is constant, and when the rate of change is constant, the average is just the minimum plus the maximum divided by 2. It's kind of like how v initial plus v final divided by 2 is equal to average velocity when you are under constant acceleration. It's the same idea. It's the same idea. So if I had, and this leads into something I didn't talk about, dams. Dams are built so that their bottoms are thicker than their tops, and that's because there's more pressure at the bottom than there is at the top when they're blocking a bunch of water. There's going to be some pressure here, and then more pressure here, and then even more here, and then even more here, and more importantly, force due to that pressure. And yeah, you want the bottom to be thicker, made of more and stronger material so that it can support more pressure. That's the basic idea. So because this increases linear as you go deeper and deeper, you can just say the sum of the force at the top plus the force at the bottom equals the sum of the next force from the top plus the next force from the bottom, and so on and so forth. So if it was like, if this started at, we need to take the atmospheric pressure into account, of course. If this started at, I'll just make up arbitrary numbers. If this started at like 5, then this would be, let's say 7, 9, 11, 13, right? It just increases by the same amount per, for the same change in depth. Then you could get the average as just 5 plus 13 divided by 2 equals 7 plus 11 divided by 2 equals, well, 9 just is the average. So yeah, when something varies in a linear fashion, you can calculate the average value of that thing just by averaging the minimum and maximum value. So we can figure out the average pressure being exerted on this wall by just figuring out the pressure at the top and the pressure at the bottom, and that's all we need. So let's figure out P top and P bottom. P top plus P bottom, and then we'll divide that by 2, and that will be our average pressure. And once we have that average pressure, we can multiply it by the area of this foundation wall, and that will give us the force, the total force being exerted on the foundation wall. Unevenly, of course. More of that force will be at the bottom than the top, but you know. And there is a situation where you would actually want to just calculate specifically the force at the bottom of the wall, because that's going to be the highest force, and if the material that the wall is made of, if you know how much force it can withstand, you would want to compare it against that and make sure that, you know, your material is actually sturdy enough to handle that. But that's not what the problem was asking for, and even if it was, it didn't give us the information for that. So yeah, let's figure out pressure at the top and the bottom. This would be just rain coming in from outside, so it does have some exposure to the outside atmosphere. There is no lid on this. If there was, then the water wouldn't be flowing in to begin with. So we need to take the atmospheric pressure into account. So P top is going to be atmospheric pressure, P0, P atmosphere, whatever you want to call it, plus rho G H top. Well, what's the depth at the top? Oh, it's 0. P bottom equals atmospheric pressure plus rho G H bottom. What's the depth at the bottom? That would be just the full depth, the 2.4 meters. Okay, so then P top plus P bottom over 2, the average pressure would be P0 plus P0 is 2P0 plus rho G H bottom, all divided by 2. The 2 on the P0 cancels out as it should, plus rho G, whoops, fine, we already wrote rho H bottom G, sorry about that, over 2. Well, H bottom over 2, that's just the mid-height, so that's another thing we could have done. We could just calculate the pressure at the center of this wall and use that as the average pressure. That's another, I guess, more intuitive one to remember. That, yeah, actually that would be the better one to remember. Just when you're looking for average pressure against a wall, just determine the pressure at the middle level and use that. That's actually more intuitive to remember. Anyway, so the density, we'll just assume pure water, even though rainwater probably contains some dust and stuff that it brings down from the atmosphere with it. But we'll just assume regular pure water density, and we'll assume it's at 4 degrees Celsius, even though it's probably not. And we'll just use 1,000 kilograms per cubic meter for rho. And for H, we're going to do half of 2.4, so that's 1.2, and G is just the G we have been using throughout the entire course. So P0, I won't write down its value right now, plus 1,000 times 1.2 is the height divided by 2 times 9.8. Let's see, 1,000 times 1.2 times 9.8, and then plus 1.013 times 10 to the 5 is 1.1306, I'll say 1.131, equals 1.131 times 10 to the 5 pascals. All right, so now we've got the average pressure. We can calculate the average force. Average force is just going to be the average pressure times the total area. Let me switch colors for this part. So average force, or actually, wait, no, total force rather, total force should be the average pressure times the total area is equal to this 1.131 times 10 to the 5 multiplied by, what is the area of the wall? It's 2.4 by 9.6. 2.4 by 9.6. There we go. Yeah, I prefer parentheses for multiplication. I don't know what the reason I wrote the X is because that's how it's written in the book. It mentions 2.4 by 9.6 by 0.183 and all that other stuff I read off earlier. That's why. Brain going on autopilot for a minute there. Okay, so that is everything we need. So just plug in numbers. 1.131 times 10 to the 5 times 2.4 times 9.6. And that gives me 2.6058 times 10 to the 6. They said what? They said to compare it to the weight of the water, which was in kilonewtons. So if I want to convert this to kilonewtons, I would just divide by 1,000, and that would be 2.605. Let's see. That would be 2.6058 times 10 to the 3. Hold on. Let me write it down. So 2.6058 times 10 to the 6 newtons, or 2.6058 times 10 to the 3 kilonewtons, which is also 2605.8 kilonewtons. And they said compare this to the weight of the water. The weight of the water they calculated for us. M water times G. Oh, and I guess when they calculated the weight of the water, they did use 1,000 kilograms per cubic meter. So that is what they intended. Good to know. Anyway, the weight of the water, they calculated it as 41.3. Yeah, 41.3 kilonewtons. So yeah, the force that the water is exerting on the wall is several times greater than its actual weight. If I want to just divide the ratio, because that's what you're supposed to do when they ask you, compare the value you calculated to whatever. You want to just divide 2605.8 divided by 41.3 is 63.09, about 63 times as much force. The wall has to withstand 63 times the weight of the water that could theoretically end up in there. And why? Well, it's because of the atmospheric pressure. The atmospheric pressure is most of the average pressure that's being exerted on that wall. Atmospheric pressure is 1.013 times 10 to the 5, and when we added the effect of the water, it only increased by what? So from 0.13 to 131, it increased by let's see. Subtract 13 from 31, and that's 18. It increased by 0.118 times 10 to the 5 only, which is still a lot because it's times 10 to the 5. But relative to the atmospheric pressure, it's maybe not even a 10% change, right? Let me see, 1.131 divided by 1.013. 1.116. So yeah, it's an 11.6% increase only. So most of it is just the atmospheric pressure that you have to fight against. All right, that takes care of that problem. Let's have a look at the next one, which says Blaise Pascal duplicated Torricelli's barometer using a red Bordeaux wine. I don't know if I'm even pronouncing that right. I don't know anything about alcohol. Never had a sip of alcohol in my life, and so help me God, I never will. I don't understand why people drink that stuff. But anyway, he duplicated Torricelli's barometer using a red Bordeaux wine of density 984 kilograms per cubic meter as the working liquid. What was the height of the wine column for normal atmospheric pressure? And would you expect the vacuum above the column to be as good as for Mercury? I kind of answered that second question earlier today. And by kind of, I mean I just totally answered it, so I gave it away for free. I should have planned ahead. I mean, I did plan ahead, it's just I forgot in the moment, and I got carried away explaining things. Anyway, so we've got a new barometer with a new liquid, evacuated tube as always, and it fills up to some height. And the density of the liquid in here, is 984 kilograms per cubic meter. Per cubic meter, not square meter. Be careful with your cubes and squares. Make sure you write them correctly on your free response, or else you will lose points. Anyway, I think, yeah, we have everything we need. We know the density, and we just need to calculate how high does it rise. It's going to be a lot more than 760 millimeters, that's for sure. So we need rho GH. Rho GH needs to be equal to the atmospheric pressure over here. I guess I drew my H. The H should have stopped at the surface of the liquid. I drew that a little off. Sorry about that. But in your drawing, if you did it with pencil, you can erase and correct it. Should be up to here. Yeah, I'll just scribble that out. Anyway, rho GH needs to be equal to the pressure on the surface is just the atmospheric pressure, so that's going to be P0. So 984 times 9.8 times H is equal to 1.013 times 10 to the 5 pascals. 984 times 9.8 is that number, and then 1.013 times 10 to the 5 divided by, and then parentheses, and then that number, close parentheses, and that's going to be 10.50. H is going to be 10.505 meters. 10.505 meters. Compare that to 760 millimeters in the case of Mercury, which is not even a full meter. Barely over 3/4 of a meter. And this one is a whole 10.5 meters and then some. So yeah, that's one reason why using wine is Probably not the best idea for a barometer. Well, it does have one advantage. It does have one advantage. Because it requires a longer column, you can measure the pressure more precisely. That is one advantage that it gives you. Because if you stretch it out over a longer column, then you can, with Mercury, when it's a shorter column, if you have a short column versus a longer column for the same amount of pressure, and I know these aren't the right proportions, but if you have a shorter column versus a longer one for the same amount of pressure, then with this one, you can cut it into smaller segments and make more precise measurements. You can measure more precise fractions of pascals off of this than you could with this one. With this one, those dividing lines would have to be much, much closer to each other, and that becomes harder and harder to read with the naked human eye. So that there is some advantage to using a liquid of lower density here. There is some advantage. It's just, where are you going to find a tube that big? That's the main issue, but if that issue is resolved, then there are advantages to be had. That being said, there was that second question. Would you expect the vacuum above the column to be as good as for Mercury? Nope. Part of the problem with that is volatility. Wine is going to have some sort of alcohol in it, and alcohols and water are more volatile than mercury, so that will interfere with the calculation. More of those evaporated wine particles are going to be over inside this column, and that will exert some additional pressure, which messes up the calculation. It messes up the measurement. Okay, what do we have next? The container is filled to a depth of 20 centimeters with water. On top of that water floats a 30 centimeter thick layer of oil with specific gravity 0.7. What is the absolute pressure at the bottom of the container? Oh, that's an easy one. It's just a specific gravity question, which we can work with. Okay, I'm just going to write the formula for this one and move on. So we have water up to 20 centimeters, so 20 centimeters of water, make sure you convert that to meters, and then 30 centimeters of oil, and then 30 centimeters of oil floats on top of that. And it's asking for the absolute pressure at the bottom of the container. It's asking for, what is the absolute pressure down here? So it would just be the atmospheric pressure plus rho oil times G times H oil, which is going to be the 30 centimeters. Again, convert it to meters. Plus, for the water, it's going to be rho water times G times H of the water, which is 20 centimeters. Again, remember to convert it to meters. And that is it. You would be done. And to figure out the density of the oil, density oil over density water, they said the specific gravity of the oil was 0.7. So density oil over density water must be 0.7, which means if the density of the water is 1,000 kilograms per cubic meter, then the density of the oil is 700 kilograms per cubic meter. And there you go. Easy peasy. Okay, here's one that calls back to some knowledge from a previous chapter. It has a drawing, so they have this drawing over here. There's a cylindrical block sitting on top of a platform, a piston. So it's inside this weird pipe tube thing. It's kind of shaped like a toilet in a way. But it's a hydraulic press. So yeah, this thing keeps going in, and then at some point there's this other disc that it's connected to. And then here's another piston. And there's some sort of fluid in here. And let's see, so it says piston 1 in the figure has a diameter of 0.25 inches. So that's this one right here, piston 1. Diameter equals 0.25 inches. So that's diameter 1 is 0.25 inches, and that's connected to, there's a hinge over here connected to this bar mechanism, and then they've drawn somebody's hand pushing on this thing, pushing it down. So somebody's hand is exerting. Let me use another color because this is starting to get messy. There's some force being applied here, force applied by a person's hand. And then it's telling us this is 2 inches. My drawings are definitely not going to be to scale here. This is going to be 10 inches. And then it said piston 2 has a diameter of 1.5 inches. So piston 2 over here, diameter 2 is 1.5 inches. In the absence of friction, determine the force applied necessary to support the 500-pound weight. So this thing is 500 pounds. And we need to determine the force necessary to support that weight. So this would have been a very quick and simple hydraulic press problem if not for the fact that we have this weird lever thing. So how do we deal with this? Some of you might already have recognized as soon as I drew this, as soon as I mentioned there was a hinge here, this is partly a torque problem. This is partly a torque problem. So all of this stuff needs to be in equilibrium with each other, right? You apply some force and there's going to be some sort of force that's exerted upward by the liquid here due to this force pressing downward. This 500 pounds presses downward onto this piston, which produces some sort of upward force over here. There's some sort of upward force over here. I guess we'll call it force hydraulic, for lack of a better term. Force Hyde is what I will abbreviate it as. And basically you want a force applied that's at least enough to counter the torque by this hydraulic force, if nothing else. Okay, so let's see what we can do here. First off, I need to determine, well, 500 pounds. Pounds are units of force. So actually, let's measure all of these forces in the units of pounds so we don't have to do as many conversions. We need to figure out the ratio of these piston areas, and we can do that by simply comparing the squares of the diameters. I need to do, let's see, the force hydraulic. So force hydraulic divided by, it would be the area of piston 1, so A1 is equal to 500 pounds divided by the area of piston 2 divided by A2. So if I multiply A1 over to the other side, then I get force hydraulic equals 500 times A1 over A2. A1 is going to be, well, you would take diameter 1 divided by 2 is radius 1, and then that squared times pi. So pi times radius 1 squared, diameter 1 over 2 squared, divided by the area of piston 2 is, wait a minute, am I doing this right? Yeah, the hydraulic force would have to be the lower one. Okay. Divided by the area of piston 2 is going to be pi times radius of piston 2, so that's going to be d2 over 2 squared, and maybe squeezing all this in here was not the best idea. You know what, I'll take this and I will rewrite it over here so that it's more legible. Okay, so the force is 500 pounds times pi d1 over 2 squared divided by pi times d2 over 2 squared. The pi cancels out, the divided by 2 squared part also cancels out. All that's left is d1 squared over d2 squared. And since d1 and d2 are both in inches, those inches will just cancel out. So it's going to be 500 pounds times d1 squared is 0.25 squared, and that's in inches squared, divided by d2 squared, that's 1.5 squared, and that's in inches squared. Inches squared cancels with inches squared. 0.25 squared over 1.5 squared, and then times 500. So 500 times 0.25 squared divided by 1.5 squared is 13 point, a bunch of repeating eighths, equals 13.889 pounds of force. Okay, and then we can take this and figure out what the applied force needs to be, because the net torque needs to be, well, 0 or a net torque that's clockwise, but net torque needs to be at least 0. So torque due to force applied minus torque due to this force hydraulic, as I called it, needs to be 0 or greater. So net torque needs to be 0 at minimum. Needs to be, I will use clockwise as the positive direction here. So distance from the pivot is decided for us. This is going to be where our pivot is. So we are 2 plus 10, we are 12 inches away from the hinge. So that's going to be 12 times force applied times sine of 90 degrees, which is just going to be 1, minus the torque due to this, minus, it'll be 2 inches away from the hinge, and then multiplied by the force is 13.889, as we just found. I probably should have switched colors here, huh? Oh well. And then 2 times 13.889, we said, times, that's also sine of 90 degrees. It's perpendicular to the distance of that position from the, or rather displacement of that position from the pivot. So 12 force applied minus 2 times 13.889 equals 0. Add 2 times 13.889 to both sides and divide by 12. So the force applied is going to be a little more than 2, which is nice. It's convenient that you don't have to put in that much force. 2 times 13.889 divided by 12 is about 2.315. About 2.315. The force that needs to be applied is about 2.315 newtons. Very nice. Hydraulic press in here, saving the day. Reducing the amount of force that humans have to put in, enabling them to get lazier and lazier and lazier with each generation. I'm sure this will not lead to any sort of catastrophic disaster in the year 2505 or whatever year it was in that one movie that some of you might know what I'm referencing. Okay. Next up. How long have we been going? Wow, almost 4 hours. Well, I guess this means that we will actually get it done in 2 streams after all. I've got just a couple more problems and then we will call it a day. So this next one says we've got a figure that shows the essential parts of a hydraulic brake system. The area of the piston in the master cylinder is 6.4 square centimeters. Let me actually draw what they have here. So they have like a diagram of a car's braking system. So they've got, like, this is where the foot pedal goes, and then connected to the foot pedal is this piston. And then inside here is going to be some fluid. And then that goes in kind of like this. And then that is connected to some other metal piece over here. Which connects to a smaller cylinder. Well, I mean, I wouldn't exactly call it a cylinder, but maybe that's because I'm just looking at a cross section of it. But yeah, it goes into this smaller one that also has some fluid inside of it. And then that connects to some sort of piston, which then itself pushes against this crescent-shaped thing, which according to the diagram is called a shoe. That's not confusing at all. And then outside of that, the shoe is touching the surface of the wheel drum, is what it's calling it. Okay, so this thing over here, I'll highlight it in green. This thing is called the shoe. Their terminology, not mine. And then the thing right outside, that's like the rim of the wheel, I guess, the metal part of the wheel. Anyway, it says, oh, and this thing is called the master cylinder. And this is the brake cylinder. This is the brake cylinder. And I don't think you need me to label this. This is just the pedal. This is the part of the braking system that you actually get to see in your car, if you have a car. Okay, so it says, the figure shows the essential parts of a hydraulic brake system. The area of the piston in the master cylinder is 6.4 square centimeters. So a master is 6.4 square centimeters. The area of the piston in the brake cylinder is 1.8 square centimeters. So a brake cylinder, 1.6, or no, 1.8 rather, 1.8 square centimeters. It doesn't matter that they're in square centimeters instead of square meters. If we take the ratio of them, the square centimeters are going to cancel out anyway. One of those instances where we don't have to convert. It says the coefficient of friction between shoe and wheel drum is 0.5. Coefficient of friction over here. Coefficient of friction is 0.5 between these two pieces over here. If the wheel has a radius of 34 centimeters, so our wheel equals 34 centimeters equals 0.34 meters, determine the frictional torque about the axle when a force of 44 newtons is exerted on the brake pedal. So force of 44 newtons is applied to the brake pedal, and we need to figure out what is the torque due to friction. To determine that, we need to figure out how much normal force is being exerted over here. And once we have that, multiply it by the coefficient of friction, and that gives us the force of friction, which would act like this, tangent to the edge of the wheel drum, which would also be perpendicular to, I guess, what we don't see in this diagram is the full wheel. The full wheel would be over here, and then the pivot would be somewhere over here if we're talking about the whole wheel. And then the radius of the wheel, we would use that as our pivotal displacement to calculate the torque. So it's going to be a 90-degree angle. So just like in the previous problem, sine of 90 degrees, that's going to be 1. So all we have to do is radius times this force once we figure it out, and that will be our torque. So torque due to friction, I'm just going to set it up in advance, is going to be the radius of the wheel times the force of friction times sine of 90 degrees is equal to 1. So radius of the wheel we have, we need to figure out what that force of friction is. The force of friction is going to be the coefficient of friction times the normal force, and the normal force being exerted in this direction is going to be the output force of this hydraulic press. This is a hydraulic press problem. So we've got force on the master cylinder divided by the area of the master cylinder equals force put out at the brake cylinder divided by the area of the piston of the brake cylinder. So it'll be force master over area master equals force break over area break. Right? Pressure in the master cylinder needs to equal pressure in the brake cylinder fluid. So force over area equals force over area. So 44 over 6.4 square centimeters, I'm writing the units just to show that they cancel out, equals force break, and I guess that's going to be in newtons, force break over 1.8 square centimeters. We can immediately cancel square centimeters on both sides. Multiply by 1.8 over to the left. 44 times 1.8 over 6.4 is... let me switch back to normal mode. Calculator is still in scientific. 44 times 1.8 over 6.4 is 12.375 on the dot. So force break, well, all that's left is newtons, so yeah, it should come out in newtons. Force break is 12.375 newtons. And I don't know why I circled that, because we're not done yet. So that force exerted by the brake is the normal force that's being exerted, is equal to the normal force that's being exerted by the shoe on the wheel drum. I hate that it's called a shoe, because I could see somebody listening to this problem without watching, like they went to, I don't know, do something else and kept this playing in the background, and they hear me talking about a shoe and they think, oh, it's the person's shoe stepping on the gas pedal. No, it's this, I guess it would be like some sort of brush thing. I don't even know. I'm not an auto mechanic, so I wouldn't know, but I guess we could probably dig up like a Wikipedia diagram of it that looks better. Who knows? Anyway, so that's going to be equivalent to the normal force. That's a force that's being exerted to the right over here. I guess it just straight up would be a normal force that this piston exerts on the wheel drum, and then the wheel drum will exert an equal normal force back on, okay, and either way, that is going to be the force that we multiply by the coefficient of friction, multiply that by 0.5, and that will be our friction force. So we're ready to calculate torque. The torque due to friction is going to be equal to radius of the wheel is 0.34 meters times the force of friction is coefficient of friction 0.5 multiplied by that normal force, which is also the force in the brake cylinder piston, is 12.375, and times sine of 90 degrees we already took care of, so put those numbers together and we get 0.34 times 0.5 times 12.375 is 2.10375. Normally I would round this, but it just looks too clean. 2.10375, and that's in Newton meters. There we go. That is what I should have circled. Just a couple more. Okay, buoyant force problem. We've got we've got a frog in a hemispherical pod finds that he just floats without sinking in a fluid of density 1.35 grams per cubic centimeter. If the pod has a radius of 6 centimeters and negligible mass, what is the mass of the frog? If the pod has a radius of 6 centimeters and negligible mass, what is the mass of the frog? I hope you remember your volume formula for a sphere. Do they even give that on the formula sheet for the AP exam? I'm pretty sure they do, but you shouldn't have to rely on the formula sheet for that. remember when I was taking like, what was it? Intermediate electrodynamics in college. And the professor called out most of the class for not remembering their volume of a sphere formula. Good times, good times. Okay, so they have a liquid, and then this frog is sitting in like some sort of bowl-shaped thing, a half sphere, and the frog is sitting in here. And I don't even know how to draw a frog. I'll just draw a block in here, and we'll pretend this block is a frog. And yeah, this sphere is just barely, just on the verge of being completely beneath the surface, in which case it would start taking on water, and then it would actually start sinking. So it's just on the verge of sinking. It's not sinking, it's just barely floating. So there's no excess above the surface, is what they're saying. Assume that the entire volume of this hemisphere is under the water, but no more than that. So a frog in a hemispherical pod finds that he just floats without sinking in a fluid of density 1.35 grams per cubic centimeter. 1.35 grams per cubic centimeter is the density of this water, or whatever it is. 1.35 grams per cubic centimeter. Must be some really salty water. Okay, we can convert this. So 1.35 grams over centimeters cubed. Well, we can say 1,000 grams is 1 kilogram. And then cubic centimeters, well, 1 centimeter, or rather, let's do 100 centimeters is equal to 1 meter. And then if I want cubic centimeters, just cube this. And that's going to be 100 cubed cubic centimeters over 1 cubed cubic meters. Yeah, and then you'll have cubic centimeters cancel with cubic centimeters, grams cancel with grams, and you get grams per, or kilograms rather, per cubic meter. That should do it. So 100 cubed divided by 1,000, and then times your 1.35. 100 cubed, well, that's 10 to the 2, and cubed is 10 to the 6. 10 to the 6 divided by 1,000, which is 10 to the 3. 10 to the 6 over 10 to the 3 is 10 to the 3. So 1.35 times 10 to the 3 is 1,350 kilograms per cubic meter. There we go. And they said the pod has a radius of 6 centimeters and negligible mass. So all the mass is just frog mass. So radius is 6 centimeters, or 0.06 in meters. What is the mass of the frog is what they want us to figure out. Okay, the buoyant force must be equal to the weight of the frog. So mg downward, buoyant force upward, and of course we're neglecting buoyant force of the air because it's probably not going to be significant for this problem. So mg equals rho vg is the buoyant force formula. Mg of the frog, well, m is what we're solving for. We can cancel the g's, and yeah, just rho times v. So rho is 1,350 times the volume of a hemisphere, half the volume of a sphere. So it's 1/2 times volume of a sphere is 4/3 pi times the radius cubed. So that's pi times radius is 0.06 in meters. So 0.06 cubed, and close that set of parentheses and close that final set of parentheses. Yep, all parentheses are balanced. 1/2 and 4 reduced to a 2, if you want to simplify a little bit. But 1350 times 2/3 times pi times 0.06 cubed. And that is 0.6107, 0.611 is what I'll round it to, 0.611 kilograms. That is a pretty reasonable mass for a small animal. So yeah, I think our result seems good. I don't see anything immediately alarming about it that would prompt me to double check it. I mean, you would double check your work anyway on the exam just because, you know, if you have the time to spare, you might as well go back. Use all of your exam time. I don't know if I've mentioned it before, but yeah, if you finish early, don't stop. Just keep going through your answers. You might catch something. So that was the frog problem. Let me see, what else do we have? We could do that one, but it seems simple enough. There was one in here somewhere. Oh, here we go. I don't want to use pink. Hold on, what color should I use here? I guess I'll use one of the darker colors. It says a light spring of force constant 160 newtons per meter. Oh yes, the springs are back. You didn't think you would see springs in fluid mechanics, but here they are. A light spring of force constant K equals 160 newtons per meter. So here it is. It's under water, is it? Rests vertically on the bottom of a large beaker of water. Yep. And then sometime later, they attach a block of wood to it, causing it to stretch a bit. And this block of wood, I guess I should have drawn the water level higher here. Yeah. And yeah, that's where the water level should have been in that first drawing. Oh well. So force constant is 160 newtons per meter for the spring. 160 newtons per meter. And then it rests vertically on the bottom of a large beaker of water, a 5 kilogram block of wood with a density of 650 kilograms per cubic meter. So M block equals 5 kilograms. Density of the block is 650 kilograms per cubic meter. It says that block of wood gets connected to the spring, and the block spring system is allowed to come to static equilibrium. What is the elongation delta L of the spring? They want this over here. What is this? They called it delta L, the stretch distance of the spring. Delta L. We've called it X and Y, or delta X and delta Y in the past. It's the same idea. We know Hooke's law. Let's use, I guess we haven't used red in a while. So forces on this thing, there's going to be the spring force and the gravitational force. So we've got force spring, we've got force of gravity, and we've got a buoyant force, force buoyant. And all of those balance each other out because this system, they said, is in static equilibrium. I probably should have drawn my buoyant force bigger to reflect that, because on the AP exam for free response questions, they will probably ask you to draw things with somewhat reasonable scale, but you know, we're still in practice mode, so we can get away with those sorts of things. Okay, what do I want to do first? So I guess I will write down my net force first. So force buoyant minus force of gravity and minus spring force has to equal, the mass times acceleration has to equal 0. And that just leads us to, of course, force buoyant is equal to force of gravity plus spring force, which we can rewrite as rho Vg equals, equals mg plus k delta L. Okay, they said that the block was 5 kilograms and its density is 650 kilograms per cubic meter. That will allow us to get its volume. They didn't tell us its dimensions, so we'll have to calculate its volume using its mass and density. So yeah, mass over volume of the block equals the density. So multiply volume over to the right, divide density over to the left. Mass over density equals volume. So 5 divided by 650 will be the volume. Actually, do we even need that? Probably not. Well, yeah, actually we do, because that's the density of the block, and this needs to be the density of the fluid. This is the density of the water. So 1,000 times 5 over 650 times 9.8 equals mg 5 times 9.8 plus k delta L, 160 delta L. Okay, the rest of this is algebra from here. I think you guys can handle the rest of this. That one wasn't too terrible. There was something I wrote on my notes earlier. Right, how high or low for the atmospheric pressure to change significantly? I will define significantly as atmospheric pressure changing by, let's see, if it's 1.013 times 10 to the 5 at sea level, then I want to figure out how high or low to change it by 1.01, change it to 1.012. Yeah, how high do you have to climb? So that'll be my made-up question, not from the textbook, but my own. At what elevation P atmosphere be 1.012 times 10 to the 5 pascals? That is my question, and it's an easily answerable one too. So you would just think of air as being part of this column of fluid. We'll make it cylindrical just because it's easy to draw. And yeah, we're looking at, so P atmosphere, we need it to change from 1.013 times 10 to the 5 to 1.012 times 10 to the 5. How high do I need to go for that difference to occur? How high do I need to go for that difference to occur? Well, if I know the density of air, which I can look up, what was it? We had it up on screen before. Let me scroll back to it. The density of air is 1.29 kilograms per cubic meter. Density of air, rho air, is about 1.29 kilograms per cubic meter. So yeah, a little more than 1/1000th of what it is for water. Okay, well, the difference between the pressure at the bottom and the pressure at the top is 0.001 times 10 to the 5, right? So you've got P bottom over here and P top over here. P bottom being just standard atmospheric pressure at sea level, and P top being this new atmospheric pressure, and the difference between the two. So the rho GH between this point and this point is just the difference between them, 1.013 times 10 to the 5 minus 1.012 times 10 to the 5, which is equal to 0.001 times 10 to the 5, or I guess if we move 3 decimal places, it would be 1 times 10 to the 2 is 100 pascals. So what height of air is equivalent to 100 pascals? Let's see, we set that equal to rho GH, and we get 100 equals 1.29 times 9.8 times H. 100 divided by 1.29 and divided by 9.8. So that's going to be 7.91 meters. H is going to be 7.91 meters. So you need to change your elevation by 7.91 meters to get, what even was that? 0.001 divided by 1.013, and then multiply that by 100%. That would be a 0.0987% change in atmospheric pressure. So it's not even 0.1% of change after rising or falling 7.91 meters. So this just emphasizes what I was doing earlier with the tube open on both sides, the U tube, the U-shaped tube. Even if there are slight differences in elevation for the air on both sides of the tube, those differences are super negligible. They were negligible in comparison to 7.91 meters, and that itself is still negligible compared to standard atmospheric pressure. So you've got a fraction of a fraction of a percent of change that we're talking about here. Very negligible. Very, very negligible. So yeah, if you have one of these open-ended U-tubes that's open on both sides, you can just cancel the atmospheric pressure on both sides. It's approximately equal. You won't see the difference for, I don't know, like a dozen decimal places. Okay, and then we wanted to do, I have this one that I think I would actually like to leave as homework, and another one that I couldn't find in the book that I'm gonna try and make up as I go, actually. So let me start with the one that I'm just kind of making up. Both of them are buoyant force problems. So first one is we have a block that's going to be half submerged. So exactly half submerged, exactly half of its volume is submerged in water. It's going to be half submerged in, this will be water at density of 1,000 kilograms per cubic meter. And we'll give this thing a mass of, what mass should I give it? Let's give it a mass of let's give it a mass of 2 kilograms. Let's give it a mass of 2 kilograms. And let's say that this block is made of wood. So let's say this is made of wood, and we'll just use the density of wood from that problem we just did with the spring. So we'll say density of water is the 1,000 that we're familiar with. Density of wood is going to be 650 kilograms per cubic meter. And the question will be, so the buoyant force from being only half submerged in water is not enough to completely, is not enough for this wood block to completely float. It's not enough for this wood block to float completely. So if I wanted to add another fluid on top of here, if I wanted to add another fluid such that this fluid would just cover the surface of this wood block, so if I want to add mystery fluid, such that it finishes covering up this block of wood, what would its density have to be in order for the additional buoyant force that it supplies to be just enough for this wood block to be on the verge of starting to float upward? That is the question. What density would this new liquid have to have? What density would this new liquid have to have in order for the net force on this wood block to be exactly 0 after taking into account both the buoyant force from water and the buoyant force from this mystery liquid. And again, this mystery liquid covers up to half the height and the water covers the other half. That is the question that I wanted you to look at. Being submerged in multiple different fluids. And then the other thing that I saw that was a really good question in the book, here's another homework problem for you. This one might be a bit of a headache, but let me draw the thing first. So there's something tied to the ceiling. They have like these hinges and supports on the ceiling, and then they have this spring scale. They have a spring scale over here. And then that spring scale supports a block. And that block is inside of a beaker. So inside some sort of container over here. And in this container there's some sort of oil. There's some sort of fluid in here. But also, this beaker is sitting on top of another spring scale. This is a compressive spring scale. So it's sitting on top of another spring scale. This one has like one of those moving needles. So it says a 1 kilogram beaker. So the beaker itself, this container, is 1 kilogram. Mass of the container is 1 kilogram. Containing 2 kilograms of oil. So the total mass of oil in here is 2 kilograms. And the oil density, by the way, is 916. So rho oil equals 916 kilograms per cubic meter. So a 1 kilogram beaker containing 2 kilograms of oil rests on a scale. A 2 kilogram block, so M block is 2 kilograms. A 2 kilogram block of iron. A 2 kilogram iron block. So I guess we'll do what? We'll look up the density of iron in a minute. A 2 kilogram block of iron is suspended from a spring scale and is completely submerged in the oil. Find the equilibrium readings of both scales. And let me look up the density of iron real quick. Iron or steel says 7.8 times 10 to the 3, so 7,800. I don't know if we need that information. Actually, I think we do because you need it to figure out the volume. 7,800 kilograms per cubic meter is the density of the iron. And the question is, what is the reading on each of these scales? What is this scale reading and what is this scale reading? That is the question. So yeah, between these two, I mean, I guess this is the easier one, all things considered. But yeah, between these two, hopefully you'll get some good practice. But I think that'll be it for today. And of course, in addition to these, you can look at more practice problems from your own textbook if you have one, or the OpenStax textbook linked in the course plan. If you are new here, the course plan is linked in the description, and if you look at the very top of that course plan, you'll see a link to the free textbook from OpenStax. It's not perfect, but it's better than having nothing. It has I think it had a few decent problems when I looked at it way back when I wrote out the course plan, so closer to the start of the school year. I might actually need to look at some of those if I run out of problems in this book, but so far I'm getting some good problems. So I don't think there's going to be a need for that anytime soon. Anyway, next time will be fluid dynamics, fluids in motion, and then that'll be the end of the chapter. After we wrap up that chapter, I'm going back to the Physics C students, just reviewing everything with the calculus added in. That'll probably be, I don't know, 2 to 4 streams worth of material, and after I'm done with them, we will have one more topic for both Physics 1 and Physics C, which is just, exam related stuff, just, additional skills that weren't necessarily covered during this whole live stream course that I've done. Just things that fell through the cracks, strategy advice where it's applicable, and just common types of problems you want to make sure you know how to handle on the AP exam, and just kind of understanding that stuff. And maybe, not promising this, but maybe I will pick out some free response questions from old AP exams, maybe like some notable ones, and we can go over how to do those. So yeah, I think that is everything in terms of announcements. I have the next session scheduled for Wednesday, but as you know, things might happen and schedule might shift around, but we'll see. I'm gonna try my best to actually just get it done on Wednesday, or maybe even move it up and get it done earlier so that I don't have to worry about something happening on Wednesday. But yeah, I'm a little bit later than I would like to be. I would have preferred to actually just be done before April started, and it looks like we're gonna be about like maybe 2 weeks late after everything's done with Physics C. So not gonna have a full month before the AP exam like I was expecting, but at least we are on track to get done before the AP exam, so there's that. That is it for me. Hope you learned something useful today. Take care. Class dismissed. I'll see you in the next one.